supposed to go stand in front of the board?
You can stand wherever you want. Because actually I'm going to...
Always going to give you the crack.
You don't need it. I got your PowerPoint up here. It's just going to do a screen share.
Oh,
So you don't need the camera.
Oh.
Infinite windows.
Can I change focus?
Absolutely.
I wanted to start rushing.
Okay, cool.
John, will I be able to do it for this?
Yes. This is you?
Yeah.
Excellent. And you want a browser too?
Yeah.
We can do that. There you go. Got your browser. You can do whatever you want there. You want YouTube?
Yeah, well, I can just pull it up from Google. That's fine.
Gotcha. All right.
Figured out the magic incantation that pulls it right up.
All right. Let's see if this guy works. Spinning beach ball of death. There you have it.
All right. So I can just change focus.
Yeah, you just
No problems.
Command tab.
Okay. Okay. All right. I'm going to start by showing you a short video, the intention of which is to motivate some of what I'm going to talk about today, because data management doesn't always sound like really the most exciting or important thing, but I think it's valuable to see kind of what goes.
Hello.
Don't do data
My name
management.
is Dr. Judy Benign. I'm an oncologist at NYU School of Medicine.
Hello, Dr. Judy Benign.
I read your article on B-cell function. I think that I could use the data for my work on pancreatic cancer.
I am not an oncologist.
I know, but I think I could use the data for my work on pancreatic cancer. Do you have the data?
Everything you need to know is in the article.
No. What I need is the data. Will you share your data?
I am not sure that will be possible.
But your work is in PubMed Central and was funded by NIH.
That is true.
And it was published in Science, which requires that you share your data.
I did publish in Science.
Then I am requesting your data. Can I have a copy of your data?
I am not sure where my data is.
But surely you saved your data.
I did. I saved it on a USB drive.
Where is the USB drive?
It is in a box. It is in a box at home. I just moved.
But can I use your data?
There are many boxes. So many boxes. I forgot to label the boxes.
Hello again. Thank you for sending me a copy of your data on a USB drive. I received the envelope yesterday.
You are welcome, but I will need that back when you are finished. That is my only copy.
I did have a question.
What is your question? You might find the answer in my article.
No. I received the data, but when I opened it up, it was in hexadecimal.
Yes, that is right.
I cannot read hexadecimal.
You asked for my data and I gave it to you. I have done what you asked.
But is there a way to read the hexadecimal?
You will need the program that created the hexadecimal file.
Yes, I will. What is the name of the program?
Cytosynth.
I do not know this program.
It was a very good program. The company that made the program went bankrupt in 2007.
Do you have a copy of the program?
I do not use this program anymore because the company that made it went bankrupt. Maybe you can buy a copy on eBay.
I have good news.
You again.
I talked to my colleague. She knew a person with a copy of the software.
Then why do you need me? Everything you need to know about the data is in the article.
I opened the data and I could not understand it.
If you have the program, you will find it is clear.
Well, I noticed that you called your data fields SAM. Is that an abbreviation?
Yes, it is an abbreviation of my co-author's name. His name is Samuel Lee. We call him Sam.
I see. And what is the content of the field called SAM1?
Ah yes, SAM1 is the level of CXCR4 expression.
And what is the content of the field called SAM2?
That is logical if you think about it.
What is the content of the field called SAM2?
I don't remember.
What about SAM3? Is there a guide to the data anywhere?
Yes, of course. It is the article that is published in Science.
The article does not tell me what the field names mean. Is there any record of what these field names mean?
Yes. My co-author knows what the content of SAM2 is, and SAM3. And SAM4.
Can I talk to your co-author?
I'm not sure.
I would very much like to talk to your co-author.
Well, he was a graduate student. He went back to China 2 years ago.
Can I have his contact information?
He is in China. His name is Sam Lee.
I think I cannot use your data.
You could check the article to see if what you need is there.
Please stop talking now.
All right. So I really like that video, and it's gone around quite a few times here at TACC, and I think there's a couple of things about it. First of all, I think it does a really good job of walking through a process of why is data management important. People actually want to use your data, and it's not just the things that you share in a paper that you write or an article that gets published. They need more than that. They need a lot of context, and you have to plan for these things, and it also kind of shows how things can go wrong if you don't do these things and if you don't do them up front. Data management is not the most exciting topic, but it is one of the most foundational in terms of being able to execute research programs, share data with other people, make your life easier over the long term. So what I'm going to do today is kind of just introduce data management planning, what it is. I always try and couple that to execution because the grant agencies required data management plans starting a few years back, and so at that point everybody started thinking, well, how do I write a data management plan? And I said, well, you just write down your plan. Nobody has a plan, right? And so it's really about the data management execution and knowing what it is you're going to do, and then the process of writing the grants and all that stuff is relatively easy once you have a plan in place. So we'll talk through some of the general principles, simple things that you can do, things that you need to think about when you're thinking about what is the most effective way to manage my data. But it's not going to be a how-to guide. I'm not going to walk you through specific applications or show you how to do specific things because these are principles and mechanisms that should be applicable kind of regardless of what system that you use, whether you're doing high-performance computing simulation kinds of activities, whether you're processing, doing data analytics on financial data, whatever it is, these are kinds of things that are going to be important to you. One of the things we emphasize in relation to data management and data collections is that these are evolving processes, right? As you're going through a research process, you're accumulating more data, you're maybe changing the way that you're accumulating data over time, maybe you're gathering more data. The whole process is evolving constantly. And in particular, given technological advancement, things like the fidelity and the kinds of data that you can generate may change, and may change dramatically even over the course of a couple of years. And all of the technologies around that are also obviously changing. I'm sure you've heard of big data as kind of a buzzword, and associated with big data are, probably hundreds of startup companies, thousands of open source software packages, any one of which may be catching on or in the process of dying at any one time. And over the course of a whole research life cycle, you're going to use multiple systems, multiple tools, different kinds of software packages. Some of them will be open, some of them will be closed. And over time, kind of what you're doing when you're dealing with research data is you're going kind of through a process of refining and transforming, right? So you're initially collecting this raw data, and then you're applying things like quality filters and throwing out useless data, and then you're focusing in maybe on a portion of the data that's of most important to you, and kind of refining and refining, and in many cases transforming things to make them more usable. And that's kind of what we mean when we talk about the data lifecycle. It's not the case that you just generate a file and then you're done with it. You're going to change what you want to do with it. You may transform it in different ways. You may want to share it with somebody else, whether that's somebody across the lab or somebody across the world. And how do you do that? And how do you know that you're going to be able to do that without having the kinds of conversations that you just saw? And I really want to emphasize this aspect of thinking about it at the beginning of the research process and carrying it through the whole life cycle. Really, I think this is what this slide is about. What this is really about is making your own life easier, right? So, again, in that video, the PI, the person with the data, wasn't being particularly helpful, but it was still messing with their life. And the third time the person came back, it's like, oh, yeah, again. Right? People are going to want your data, and they're going to want to do stuff with it. And you're going to have some kind of an obligation to help them with that, even if it's a very minimal obligation, or even if they are just very persistent about wanting to use your data. And of course, your own research processes, you're going to be generating these things and reusing them. If you go onto a system like Stampede and run a large simulation, you could be generating 1,000 files per timestamp. You're doing hundreds of timestamps. You can get 100,000 files in no time on a system like Stampede. 100,000 files. You want to have better ways of organizing and locating data within those 100,000 files than, well, I knew I put it somewhere. There's just a million files I have to look through, and somewhere there it is. And so, really, it is about having these processes defined ahead of time so you can kind of smoothly go through your whole process, and you know what you're doing at each step and what kinds of things you need, and then you'll be in a good situation when you get to the end of it to put it out in some location where you can share it with other people and you don't have to deal with lots of questions, or you can relate it to other pieces of data and it will be useful without significant extra work. So the process of making a data management plan, I would say, if you're considering doing research, particularly research using digital resources, get in the habit of doing these data management plans, even if you're not writing grants that require them at this stage, because sooner or later you will if you're going to do that kind of thing. And even though the grant agencies require these things, I'm going to go back to what I said earlier. This is a tool for you, fundamentally. It's about making your life easier. It's not just about satisfying the granting agencies. If you've done it in such a way that you've made your own life easier and accomplished your own goals, you can just write that down, send it to a grant agency. They'll be very happy with it. So these are some of the things to kind of think about. In any domain of science, there's going to be best practices. There's going to be existing standards. Different kinds of sciences have different kinds of data that they deal with, and they've developed common standards. In some cases, very robust, long-lived standards. In some cases, very dynamic. Kind of depends on the discipline and the interaction with technology. Do you plan on reusing the data? How do you plan to use the data? In the simulation case, it may be that you're generating lots and lots of intermediate files, but you're not actually going to use most of those. You're only interested in, maybe a 10% sample. You can throw the rest of that away, and you don't necessarily need to worry about it. But if you want to maybe share it with somebody else, and somebody else could get some value out of it, maybe it's worth keeping, even if you are not planning to use it. Think about the storage and computing resources available to you. A system like Stampede, again, has 3 file systems within the cluster, at least 2 or 3 additional file systems that don't live in Stampede, but you have access to from Stampede. And just as an example, obviously there are systems that big tape archives like Ranch, and then commercial solutions and other things. Provenance is a really kind of increasingly important thing, and in general what this means is just tracing where something came from and what steps it went through to get there. So this is, provenance is a term that comes from things like archival and library sciences. It's applied to documents, who initiated this document, who had it in between, did somebody fake it, those kinds of things. In the digital world, it's about which tools did you use to create a piece of data, what did you do to modify it over time, and this is really crucial to reproducibility, which is something that is increasingly worried about in the computational science world, because that's something that's really key, fundamental to science, particularly in things like wet labs. Reproducibility is absolutely essential. In the digital world, we've been doing simulations and analysis and all these things for a very long time. We haven't spent a lot of time worrying about how do we reproduce these things. And it's very common for software versions to differ between different platforms. Different people use different tool stacks. Some of those tools are commercial, and someone else may not have access to them. So it can be very difficult to think about how would somebody actually reproduce what it is that you've done and show that what you've done is actually valid work, right? That's how science is validated. And then, of course, what publications you're going to get out of it and what requirements there might be associated with those publications. They talked about science now requires that you make your data available when you publish something in Science, although it just means that you have to have something available, not necessarily that it has to be complete or useful. So I've already mentioned there's lots of different data types, lots of different data structures and functionalities. This Institute of Classical Archaeology collection is kind of a good example that shows this. So this is a collection of essentially objects and events from archaeological digs. And so they're taking things like images of bits of pottery that you found in a dig, associating that with, say, GIS records, so you know exactly where that thing was found. Maybe structured data, database fields that describe different interesting aspects of that object, and then all of this can be overlaid on maps. So you've got lots of different kinds of data that needs to be related to each other in a collection in order to actually extract meaning from these masses of data. So here's kind of a taxonomy of data types, different degrees of things like stability. Obviously, is if you're taking a measurement of something and you have confidence that the measurement was accurate, it's not going to change, and it could have value over very, very long periods of time. So a good example of this is climate change. Science has really benefited from simple meteorological readings that were taken by navigational stations over the course of the last 150 years. And the reason that they took those kinds of readings and recorded weather conditions is because they were required to help ships navigate. That data, though, is very, very, very stable, right? If it was true about that one point in time, it's always true about that one point in time. And it turns out you can reuse that data to look at how has the climate of different areas changed over time, over very long periods of time. So that's kind of observational data. Experimental data is really kind of a variation of observational data. You're setting up a situation in an experiment, and then you're observing what's happening. And then there's various kinds of derived data, things that you generate by doing statistical analysis, reducing data, throwing out low-quality data, those kinds of things. Simulation data, obviously, is where you start from first principles and you say, well, this is our mathematical model of the world, and we're going to try and simulate that and see if that matches our observations of the world. And that may or may not be valuable over the long term, depending on what you're doing. Right? You could run a simulation today and then tomorrow discover that there's a principle you hadn't included in that simulation, and it turns out all that data is useless because you know it's wrong, or it doesn't match the observations that you have in the world. So that can be very ephemeral. And it may or may not be very costly to generate. With supercomputing, with simulation data, some things require a few hours on a single machine. Some things require the entirety of Stampede for, say, 12 hours. Then you're talking about hundreds of thousands of dollars that actually go into generating that data. And then, of course, software. And software is a very interesting kind of case because in some sense, you want software to be stable. Right? You want Photoshop to always be Photoshop, but it also evolves and changes over time. Formats associated with that software may change. You may have had the experience of having someone send you something like an old Word document and you can't open it because Word doesn't support that format anymore. So I'll talk a little bit here about data storage systems just to kind of emphasize a couple of points. It's important to understand at least roughly what the metaphors that different storage systems use, and that they are fundamentally metaphors, right? At the very basic level, there's a lot of stuff happening. Just as with compilers versus machine language, the way that bits are actually laid out on physical spindles, magnetic media, and how that's spread across maybe lots and lots of spindles is not something that you want to be cognizant of and be thinking about. So we have all of these different pieces of software that we call things like file systems or databases that fundamentally are about creating a metaphor for how you're interacting with data and providing you an interface that makes it easier than what particular sector on a disk platter something is stored on. So there's things like file systems that generally operate at the operating system level. So Linux has things like ext2, ext3, if you've messed with Linux much. Things like databases, which databases may sit on top of a file system, but they don't have to. If they do, generally what they're doing is they're just creating one big file that represents a database, and then the important thing to recognize is that the database software itself is doing a lot of management of that data within a big file or even just a big partition. There's different kinds of distributed storage, so something like the Lustre file systems that live on the big clusters here are distributed storage, and those are, again, very complex systems where you've got lots and lots of systems with lots and lots of drives coming together, and again, you're usually using a file system metaphor to present it, so from your interactions with it, it looks like it's the same thing as a disk sitting in your laptop, but obviously there's a lot of hardware sitting behind it. And then there's all of these different kinds of analysis tools, which may utilize all of these different storage protocols, different pieces of the software stack, and you have things like MapReduce and Hadoop that kind of incorporate a distributed storage model into the analysis mechanisms. So I just want to point out that file systems, we've gotten so used to file systems and having these hierarchical ways of storing data and working with folder metaphors for everything. We kind of think of it as like a natural thing, but it really is just a metaphor. It's the way that we've chosen to organize things, and you see people thinking about different ways of organizing data now, organizing them around tags and things like that. But because we have so much existing infrastructure and history of working with these kinds of hierarchical storage systems, they're not going away anytime soon. But it is important to recognize that this isn't a literal representation of how data is stored, and you can do whatever you want with how your data is organized, or you can lay systems on top of it to provide different interfaces to managing it. And like I mentioned before, these technologies operate everywhere from individual laptops or USB keys have a file system on them to continental scale. I operate a file system that includes hardware resources in San Diego and Illinois and Pittsburgh and here. So this may or may not actually be the right metaphor for working with your data, but you have to understand what some of the kinds of limitations are with it. So one thing to do would be to say, well, my data isn't hierarchical. It's just all a bunch of data that's directly related to each other. So I'm going to put it all in one big directory. Besides organizational issues with that, there are technical limitations with the way that the file systems manage the data. If you put 100,000 files in a single directory on some file systems, and then run an ls command, you're going to sit there and wait for a couple of minutes before you even start seeing data. And then you're going to see 100,000 files come out in one big listing. What are you going to do with that? So it's important to sometimes understand how the file system technology works, what the limitations are, and again, what are your cognitive limitations in terms of how many files do I want to look at in terms of picking out something meaningful from a directory listing. So relational database management systems. David may talk some about these and some about related systems. These are really fundamentally about dealing with structured data, data where you have a really well-defined structure. It could be in something like single records, like the classic example is the address book. Everybody's got a name, everybody's got an address, everybody's got a phone number. So you know that there's going to be a structure to the data. And if you know there's going to be a specific structure to the data, and you tell the system what that structure is, then it can optimize the way that it stores that data such that you can do things like search it really, really fast. So, banks use gigantic, very, very optimized relational database management systems because financial records are all very, very structured, and you need to be able to search them and pull data out very, very fast. So you can do things like say, give me all of the transactions that are associated with this account over this date range, and a database system that's well-tuned can give you that answer very quickly, even if it's having to search terabytes and terabytes of data to do it. So these kinds of transactional scenarios, that's another aspect of it if you're dealing with highly structured data. How you manage updates to that is very important. And again, if you think about the financial world, if you're transferring data from one account or transferring money from one account to another, you want to make sure that you don't say, okay, plus this account $100, and then have something go wrong that doesn't minus another account $100. Because what happens, you've created $100 out of thin air, and banks really don't like that because then they have to pay somebody. So these kinds of transactional consistency scenarios are very important with relational database. And you can also impose limits on data. So it's really nice if you have certain restrictions that you want to apply to data. If you want to say, well, this data can be of the value 0 to 100, but if the value is 200, then it's clearly wrong because it should never give me that value. You can put that into the database so you know that it won't ever store bad data for you. And that kind of thing can be very, very valuable, especially as you start getting lots and lots and lots of data, or you're doing something where you're pulling in thousands and thousands of records an hour. Again, financial systems, weather monitoring, those kinds of things. You don't want to have to manually review and say, does this data make sense? If you know what is sensical and what's not, you can just tell the database system, and it'll enforce those things for you. So that's really valuable. And you can do some really interesting things with creating schemas and how different pieces of data relate to each other and how you index things depending on how you want to search this data. So I would definitely encourage you, if you work in an area where you have lots of structured data, something like finance or business, to spend some time learning about these systems and how they work, because there's really some amazing functionality. And a lot of these are used in analysis workflows, although some of it may be file system data, but again, economists do a lot of analyzing the last 100 years of stock market data. That's all done essentially in a database. What you do is you use the database to pull a subset, the data that you're interested in, into a tool like MATLAB or R that David will talk about, and then you're able to do statistical analysis on the pieces that are important to you. And if you know what your workflow is ahead of time, what you're going to do, you can automate these kinds of things so that you could, just have the system automate all of the data collection, the analysis, and the reporting, and just email you, here's the latest thing that the system learned. So I think I've talked a little bit about data organization, things like folders. I think the key thing here is, I mentioned you're thinking about your own cognitive limitations, how much data you want to deal with, but also think about whether the structure that you put into your data makes sense to somebody else, right? Don't use the name of your collaborator as a folder name, because that doesn't mean anything to somebody that's not you, right? And this is something we talk about as hidden knowledge, right? So you see here's an example of the kind of file name that you could very well imagine seeing, and I think this is probably a real example. And each one of these little pieces of the file name, so CXT25497, that's probably a code for a specific thing. But what is that thing? Well, it's not clear. You could very easily change the way that you're doing things like file naming and folder naming such that it's much more obvious what it is that you're doing. And that's one of the kind of key things to think about. Think about that hidden knowledge. Where are you hiding things based on the knowledge that you have in these complex spreadsheets, file names, whatever they may be. And that's particularly key if you're going to share your data with anybody else. And actually, I think this source code documentation is a pretty good example. This is an area where people have mostly understood and developed good practices around things like commenting, the way that code is structured, right? Just the way the code may be indented, depending on its location within the code, commenting. All of those are the kinds of things that are meant to surface the structure of the code so that when you visually look at it, it's really clear what's going on. Or you can go and look at what comes out of an obfuscated Perl competition to see the kind of bad scenario. And the end result of this is you have data that you can easily share, you can maintain it. 5 years later, when all of your grad students are gone, you'll still know what's in there, and you can still use it for analysis again in the future. Metadata is a really general term that we use to refer to all of the stuff that's about the data. So this can be the technical stuff like what's the format, the size, what camera did I take it with, all those kinds of things. A lot of times, tools like HDF5 will automate some creation of technical metadata for you. But this is really important if you're going to do preservation, or really even over the long term. If you're going to change the set of tools that you use and you want to be able to pull in the data into a new tool, well, what format is it in? What are the relevant aspects of it technically that make it readable? And then things that we call descriptive metadata. What's this about? Who created it? When was it created? All those kinds of things. And then there can be issues like administrative metadata. Who owns it? Is there a license associated with it? So if you have a particular license, like the BSD license, you could put that into metadata. And then provenance, which I talked about already. And the key thing here is just that there is lots and lots of metadata that you could have, but what's the important stuff? And just do that and do it consistently. Because if you don't do the same things to all of your data, then stuff's going to get lost. That's just the way it happens. Right. So here's just an example of structured metadata. This is XML. I won't spend a lot of time on this, but the basic idea is, it is structured, right? We want to have consistent fields from file to file. If you don't have consistent fields from file to file, then you don't know what to look for in the metadata, and it's almost not valuable to have created it in the first place. So just a little note about archiving. I think it's important to think about where is the data going to end up at the end of the process, and particularly if you intend to share it. Using these domain-specific repositories is really valuable. In the biological world, there are big repositories for, say, genome sequence information, and you can contribute to those repositories. And increasingly, NSF is trying to give people credit for doing things like contributing to those repositories or producing shareable data. So if you get in the habit of doing this as a researcher, this will actually really I think facilitate your career over the long term. But these do tend to be static, right? This is a way to say, I'm done with this data, I trust this data, I believe it's good, I'm going to put it up in this shared location where everybody knows to look for it. And the other nice thing about that is then you don't have to worry about it anymore, right? You're no longer responsible for sharing that data with other individuals, but you're giving up control as well. So there's another model where it's essentially the one that we just saw. You wait for somebody to come and ask you for it, but have more than one USB drive if you're going to do that. And then there's things like cloud storage, and essentially what this really means is just that you have some kind of off-site location that you're likely contracting with or have some kind of an agreement with, and they're going to kind of handle storing your data. And there may be multiple levels of service here. Something like Amazon Web Services, it's just give us your bits and we'll store them and we'll give them back to you. There's other services like DuraCloud who will actually provide a preservation interface, do some of the metadata processing, provide search functionality, all those kinds of things. So it really just depends on what you want there. And then there's lots of different systems in terms of kind of technical systems and places like TACC that can provide different kinds of interesting storage, both for things like high-performance data analysis, and things like long-term preservation. So transferring data, I'm not going to spend a lot of time on this, but I just want to kind of mention it because it is something that gets a lot of attention. You know, a lot of times when you're dealing with lots of data and you're doing different kinds of research tasks on different systems, you're going to end up spending a lot of time moving data around, especially in the context of something like Exceed, the big national partnership that provides computational resources. You may move from one site to another. And if you built up a lot of data, that can be really time-consuming. And there's lots of different ways available to do that. And you know, providing a really easy-to-use, easy-to-set-up, high-performance data transfer tool is kind of like a holy grail of cyber infrastructure that probably will never be achieved. So in reality, what really happens is that if you want to get higher performance in data transfer, you're going to spend more time setting up the tools and watching the tools and picking configuration parameters, essentially to get the most out of the storage system and the networks that are involved. And so what I generally tell people is, you know, start with the simplest thing, start with something like SCPs, graphical client, just try it, see if that performance is acceptable to you, and if it is, then great, you're done. Try the easy thing first before you spend a lot of time trying to get the maximum performance out of the network. You'd be amazed how few people do that. Okay, just a few things I want to kind of call out, think about. Confidentiality. If you're dealing with human data of any kind, this is really, really crucial, and it's evolving. You know, what is data that's subject to HIPAA protections, what's considered personal health information, is evolving, right? Because it used to be your medical records, but then people figured out that you can, you know, do some reverse engineering if you have somebody's full genome sequence information, and actually, in a lot of cases, figure out who they are. So there's these questions about, is genetic data actually something that should be subject to special protections in terms of privacy? Because people can find out really private things about you by looking at your sequence information. And of course, FERPA is something, as a member of a university, FERPA is directly relevant to you. There are laws that regulate what people can say about students. And there are these things called IRBs, institutional review boards. If you're dealing with human sources, and in many other cases, you have to go through an IRB. And basically, this is just a group of peers who review what you're doing and say, yes, they're not trying to poison toddlers just for the sake of poisoning toddlers. There's really something meaningful that they're doing here, and they have good controls in place. But these are things that you're going to have to think about and incorporate into your data management, right? The way to protect sensitive data is to make sure that it's protected from the very beginning. They have a plan for where it goes, who has access to it, make sure everybody understands those rules. You know, if you're dealing with really sensitive data, don't start sharing passwords around. Simple things like that. Understanding those kinds of things is very important. Similarly, intellectual property rights. Obviously, software is kind of the big one in this area because there are different licenses that are associated with software. Sometimes you have to pay. Sometimes there are different things that you can and can't do. So you need to be aware of that. But then there's also, you know, if you're dealing with different kinds of humanities research, you may have images and video that are subject to copyright. You may have different kinds of patent restrictions on data. And even, you know, in things like the financial world, again, a lot of data is made available only under very specific licenses for very specific purposes at very specific times. So you have to be aware of that. And again, if you need to have access to a certain kind of data, you need to know are there licenses associated with it. Can I get access to it? Will it cost me money? If I then get access to it, can I do anything useful with the results, or are there actually restrictions on it? So, for example, Twitter. You can get access to Twitter data, but one of the things they often want you to do is submit your research to them for review before you're publishing it. So you have to think about, is that really a condition that I want to submit to? What if I find out something that's not flattering to Twitter and they say you can't publish this? Then you've just wasted your effort, basically. Because you can't violate the terms of the license that you've already signed. You can't go back and say no. That doesn't make sense. And interoperability. And there's some kind of interesting, really interesting questions in here about data structure and standards and what counts as intellectual property. And of course, patent law is constantly evolving. Preservation. So I already talked about how data can be useful for purposes that you didn't even consider over a span of literally hundreds or thousands of years. And so one of the things that's an area of a lot of activity and research right now is how do we preserve digital data for thousands of years? Because it's easy when your information storage mechanism is stone. You can just leave it sitting there and it's not going to degrade. When it's very, very delicate, very micron scale bits on a piece of magnetic media, you can't just let it sit there. After a few years, it's gone and you can never get it back. So digital preservation over very long periods of time requires constant awareness and active management to move things around between systems, to make lots of copies, to make sure that you have lots of copies, to make sure that what you have now is the same thing as you had 10 years ago, because you can have things like cosmic rays that go in and just change bits randomly. And depending on the type of data, that can have very little impact, or even a single bit or two can make the rest of the data completely meaningless, depending on, again, the structure of the data and which bits get flipped and all those kinds of things. So there's a lot of work here. Most of it is not things that you need to be aware of, but doing things like picking an open repository that is responsible and will do the sharing of your data is a good step towards that, because then again they take responsibility for the data, and they because they're all dealing with the same kinds of data, they can deal with issues like, is this format going out of date? They understand the importance of it and they'll take care of it over the long term. And then there are projects, and a lot of universities will have their own systems to provide long-term preservation. Won't spend time on this slide. And here's just another kind of example of one of the things I haven't talked about too much, but it's very unlikely that all of your data is going to be of one type, and this is where data management becomes very important. When you have lots of different kinds of data, again, here's an example where you've got images. You may have genetic sequence data associated with particular plant or animal specimens. You have information about where and when it occurred, all of those kinds of things. And you have standards for sharing this data as well. So again, lots of different pieces that can't be stored in the same system or can't optimally be stored in the same system. So you have to come up with schemes to relate different kinds of data together to transform it into open standards for sharing it. And so forth. Then there's some really interesting examples of things that people, again, have done with these kinds of collections, taking genetic samples of very old specimens to actually determine things about how evolution has happened over time in certain areas, because they have these very old specimens. And if you can extract genetic information from them, you can, again, do new science with old data, essentially. So just quickly, some of the options available. There are kind of very few really long-term storage options, kinds of reference collections. Projects like Exceed, the project that Stampede is a part of, and Branch will provide things like tape archives, but there's not a lot of guarantee that you're going to have a long-term storage capability on a system like Branch or Stampede. A system like Stampede, its lifespan is going to be 4 years, maybe 8 years at the outset, and then it's gone. You're just going to tear it down and throw it away, or give it to somebody else, and so you're not going to store data there for a very long time. So these reference collections I've already talked about, and in some cases they're really project-specific kind of resources. There's a project called iPlant that provides storage and computational resources for plant biologists. So again, take the time to look around if there's a particular discipline you're working in. A lot of times there are resources that are available to you for free that are funded by NSF or NIH. And every institution, including UT, is dealing with this vast increase in digital data. in different ways. UT is lucky to have TACC, so we kind of are able to handle a lot of those requirements. Other institutions may provide their own options. Some of them will be free, some of them will cost. You can run storage yourself. I think there's almost no situations in which that's the best solution. And unless you're a computer scientist, your job is not to run computers. So why would you do it? That's you're not going to go and start maintaining the plumbing in the bathrooms. Why are you going to start running computers if that's not what your job is? It doesn't necessarily make sense, but you can do it. You can go out and get lots of USB keys and put all your data on them. Cloud storage, the thing I just want to mention about cloud storage is it's not entirely clear what cloud storage is. People have different ideas about what constitutes cloud. Some people talk about cloud like, well, I've got a storage system, so that's my private cloud. Some people talk about it like, well, I'm buying storage from somebody else and I'm not operating it myself, therefore that's cloud. And it can be either of those things. There are technical implementations of things that are cloud storage. Usually that means an object store if you're talking in technical terms. Again, these are very contested kind of terms. But there are commercial offerings that are useful. Things like Amazon Web Services can be a useful, at least complement to resources that you have yourself or resources at TACC. I always tell people don't store all of your data in the same place. Make copies of it, because something can always go wrong with any system. We can be the most sophisticated managers of our systems in the world here at TACC, and we can still have a bad weather event or a meteor or something, and it just wipes it out. And it's relatively simple to protect yourself against those kinds of things. And cloud storage is a good option for that if you can afford it. Usually it's not too expensive to just store a bunch of data in a cloud provider, but if you want to then pull it back out or share it with a lot of other people, they'll usually charge you by the access. And that can get very expensive very quick. And since these data management plans have become required for grants, most organizations that rely on grants for support have started trying to come up with strategies to figure out how to help people write them. UT is one of those. The university library at UT and at a lot of other institutions will have some resources for data management. And again, if you think about it, librarians and archivists have been doing data management for a really, really long time, just not in the digital world. So they have some useful things to say. There's TACC, there's other sites within the NSF framework that have similar kinds of services, both in terms of helping you develop data management plans and then in writing them down and communicating them to NSF. And of course, in integrating those within the overall context of a computational environment of cyber infrastructure. May include visualization, may include different kinds of data analysis, simulation, all those kinds of things. And that's good for now. I'll answer any questions that you have. I know it's still early. Yes? Yep, so SQL, the structured query language, is pretty much the standard mechanism for interacting with relational database systems. So MySQL is an example of an RDBMS. The interesting thing is there's these new technologies that are called NoSQL that in many cases actually still do have an SQL interface to them, but store data differently, or they can do what's called semi-structured data, and something like a web page would be a good example of that, where there's real specific structure. You've got a title, you've got a body, you've got defined elements within it, but how many of those elements you have and how big they may be can change. And so the NoSQL options provide a similar interface for data like that. Okay, anything else? All right. Well, I think you've got 10 extra minutes. I tried to keep it light. I know it's been a long week by now. Yeah. We better have quite a song and dance prepared, David. So I think John is going to give you a tour in about 10 minutes.
We mostly on it's called corral, so 4 petabytes. Actually, it's 10 petabytes raw, but it's 4 petabytes capacity. So what I have is yeah, I think it's a good idea as part of the overall strategy. I wouldn't say put all of this but if you've got a local copy, that's a good strategy. Yeah, so that's something I do. Copies on speakeasies. I've got a laptop, that's the primary. There's also some music services. Yeah. Well, I mean, so, thank you. Please, David. Please. This is hilarious.
I'd be happy to use it.
No, that's all right.
Oh, yeah, I have a
Too much download or
Okay. Go online then. Well, I'm definitely putting that.
Are y'all still keeping the reality or?
That's not bad.
Wow.
I have 240 undergraduate. No one took that before. Yeah.
Hey, no. Add or two. Talk real fast. That number on the note.
You go back to the
And then just stop it.
Cease restricted and waiting for.
You gotta.
So
Oh, wait,
yeah. Sorry.
That's why I just got.
No.
Yeah, you can shit
I like that.
It's like all yesterday we're going off and someone was talking and I was just like, what?
Yeah.
Is that gonna be in here?
If you're on your laptop.
You know what I mean? I wanted to sample and start reading this. I just did this. Oh, thank you. The writing.
You realize I don't like that.
I just thought you were really stupid. You Like all my friends with them.
Oh, yeah. That's like,
Or like you just like.
yeah, that was my issue. Something like this. One sheet for me. It's like another word. Why are you a cat?
That was my picture.
Why are you a cat?
I thought it was funny. This is so awkward. So that's my picture.
First off. Oh, and another thing. I was watching TV. Things like this. They were filling it. I was like,
Yeah, you
Thank you.
thank you. Zach. Did they call you?
Hi. Y'all have short? Yeah, what time? Yeah, we'll wait a chance.
Oh, but you were her, right? Everybody else right here? No, but she took forever on first code. She gave us like 3,000.
Okay, I'll pop back down, we'll go down.
Everyone, tell me about that.
Couple minutes.
I feel like I'm gonna memorize that little short little program forever. Just the first code that speaker on that forever. Oh, and then when she got me trying to run out of the class, we were trying to get she was like, yeah, you know, like, and we wanted to run out one class. I just love that she would smile. She'd be like, yeah, and if you answered it that way, I'd give you an F. And she was
All I have to do is just reply back to the email.
Because I need more than just being honest.
No, and then the whole thing just like cracked me up. I didn't even know he heard me. He was like looking at her. He was like, I don't like you. He's like, I'm not gonna take it because I don't like you.
Wow.
But my favorite is she was my favorite. She was like, zero. Like a big smile on her face.
Yes.
And you were like, where's my napkin?
Why? I can direct message. Oh no.
It's
like a penguin.
So is this a Snapchat?
Yes. I think it was that time.
That's how we're painted.
Guaranteed you can do that same thing. Guaranteed. Nothing's gonna change.
So fair how I retain all my portraits.
You retain more than I did now.
The only thing that confused me was I think it felt like being able to have it too.
Okay, maybe someone
That's
took them to do it, so they can do an experiment.
I know. But then at the SE showed the for all, I was like, why?
That was my point. I was like, oh my god, if I had learned that earlier in the classes, and you know what? I think professors like speak self-esteem
Yeah, I'm saying.
for their own satisfaction.
Jesus.
Because now I'm looking back, yeah, I should have learned more here inside because like what for that nasty money I would have.
Yeah. I mean, I feel like if you put some time, you could do that in like 2 years. Well, if you get your coffee, I'm gonna take this too.
But the thing was
No,
so
because I bought
cool.
this. I thought you said you wanted me to have coffee.
No, I.
Yeah.
You just picked up
I can feel it. I was like, why would you want more? I was gonna take it down. I did just let you know.
That's fine.
That's great.
The coffee's alright.
Because you haven't touched it by now.
You guys, I can't. He even said that he knew this topic before.
I was just hard.
Yeah.
You knew that this year was
I'm so bad. They're sleepy.
Oh, I was like, wow, you just said stuff. I mean,
Because I don't want him to think it was
What is wrong with these
It's like, this guy was super popular. He's not person. I want you to know when I write those down in the steps. It was like the only thing. All there are those 5 points. And they're probably going Step 5 so disregard step 1.
What's up with these names?
You at me and you gonna be.
You were what?
Yeah,
Oh.
he's an awesome artist. You should put that in. Laughable.
Not a compliment.
Wait, is that a good thing? Laughable?
No.
Or is that like people laugh at you? Or?
Actually,
I don't
why would you
know,
want
like,
that?
what other, there's like a lot of.
That is kind of awesome. You should go with it. Straight up.
I like that.
because you were already in the second one.
They put it wrong.
Ben, stop changing your picture. Take one.
Dude, you were straight up watching that until.
You won't know.
Yeah, it's joyous. And
Okay. I want to draw everyone's attention to a document in TACC staff that says evil.sh.
Where?
Right up there, it says evil.sh.
No.
They're planning to take over the world.
I just want to highlight it so they know when they come.
I'm blind. Where is this?
It's
Go run it.
It's just in the TACC staff.
that's really funny.
Oh, that Carla.
Why?
Who is Carlos?
Who is evil?
Carlos wasn't he the dude that told us yes?
Yeah, guy named Carlos.
Oh no, his last name was I.A. Garcia.
Well, I mean,
It was that guy, the last guy. We had a
Really?
No, that was classes.
I wonder if this thing.
Oh wait, who was that one?
Are they still doing the Google thing?
Oh,
I don't want to be up here if it's the Google thing still.
no, it's not on right now.
Okay, good, because that would have
Started, then you can see yourself.
been weird.
You about to mess them up.
No, I was just looking at this page. It's up. Texas Advanced Computation. Because I want to follow them on Google Plus. Can you just search TACC on Google Plus to get here?
What are you trying to do? Where are you trying to go?
I'm just trying to follow them on Google Plus, like on my account. But you know, I'll just try it and see what happens.
Good. Just try it. I manage people. I manage nothing. My technical area Okay, so we'll go ahead and give you a tour of the facilities. My name is Chris Temple, and I'm Director of Services. And my group is responsible for all of our interactions with everything, including training. So John Lockman, training coordinator at TACC, who's one of my report. So what we'll do is, we've actually got 2 computer rooms. I don't know if any of you have been, you can eat lunch here. There's a building a couple of blocks away. There's a water tower, a building right under the water tower. It's called Commons Building. That's where we started out back in 1985, I think it was. It's where the first computer center was. And so there's still a computer room over there. It's about 3,200 square feet. And that's where we have a system called Lone Star. In fact, they hopefully talk to you about Lone Star. And the ranch storage facility. So we've got 2 big robotic mechanisms over there that can house up to 10,000 cartridges in each one. And there are pass-through boards, so the robots in there cartridges back and forth from load. So we can get a tremendous amount of data up there, but it's all taken. The cache that sits in between the users and the storage facility, and that cache appears to all of our users just like any other Unix file system. CD, copy files, etc. Files that sit in the cache will eventually migrate over onto a cartridge in the robotic mechanism. To you as a user, when you CD in your directory, there is a special option on the LS command that will show you, indicate to you that, yeah, that file is there, or it's in that directory, but it's actually gone. Any touch of that file, it causes a message to go to the robot with that tape number X, where that file resides, put it in the drive, file comes back on that cache, then you can move it back to the system that you want to use. Okay? Biggest problem we have with files that reside on a cache is that our users will tend to want to run their code using them. But that's very slowly. So one of the things you have to do is train them to move those files back over to the system that they're on. So they'll be running on a directly attached disk subsystem to get the maximum performance. And then we have some network equipment. Facility here is our almost brand new facility. That part of the computer room is about 5 years old, I guess. We built a building here, and we built that computer room. That's where our old system called Ranger was installed, and that was about 63,000 cores. Okay, 4 rows of racks. We're going to see what remains of it. We'll walk down the first skeleton of Ranger. And then when we put Stampede in, which is right across the hall, now you can see how big that system is. That's 104,000, 105,000 cores. 8 rows of frames. Okay. And it occupies pretty much the whole newer section of the computer. So when we won the award to put in Stampede, we had to expand that first part of the computer out into this parking lot. We built this room here as well. So we had about another, I don't know, 6,500, 7,000 square feet. So now in total we're looking at 13,000 approximately square feet. And then there's some other resources out here as well. Mention okay. Also, when we built the computer room, these systems require chill water. Okay, you've got to get the heat out of the room in some way. Okay? So you have to provide chill water facility to move the system. So we'll take you out, we'll go into the computer room, take you out to this facility that we built just to provide chill water to cool Stampede. The chill water out here at the facility that provides chill water to all of the buildings on campus was not enough to support all the buildings as well as support the city. The good thing about that is if we lose the plant, the center, the pickle center chill water, lose air conditioning to all of the buildings, but we'll still have ours running and Stampede will be happy.
The water cooled?
Well,
It's air cooled, but actual water sitting.
you got to remove the heat.
Indoor coolers, you'll see them.
Yeah. Yeah, we'll be able to pull a tile, we can look at it. Yeah, there's quite a bit of infrastructure that goes supporting this. You can imagine 105,000 cords running. You know what your laptop generates, right? Feel the heat. Imagine you've got 105,000 cords running. All of a sudden you lost your air conditioning or the ability to chill. How quickly that computer will do that. Probably to the point where we could start damaging. Now, I don't know if you've met Dean. This is Dean Nobles. He's been floating around. He's a retired guy who just comes back. He likes it here. So, but no, Dean has been in charge of facilities here at TACC for many years. Okay, that goes back to 85. So, he knows quite a bit about all the chilling, power required. So, okay, so let's head on out.
Lions charged right on through.
Well, you have to. You have an operational requirement. Good luck.
Sir?
Good luck.
All right.
interesting now. I don't know what changed exactly, but now I get CC on most of these tickets that come in. It's just kind of interesting watching someone. My favorite this week is the guy that was so upset with Lars for not answering his ticket, or the guy that said he had 3 terabytes in his home drive and he wants to do it. I was like, I don't think that's possible. I was a lot of them using 4 and 1
Aren't driving actually. Fine. Fine. How often? You fix that. You can change the functionality of the system so that that can happen. Or you can change the strings, which startups. It's no longer possible to submit a job. You build one API stack out of it. I run it. You have to do that. That's it. It's no longer possible for us to our sake ways to spend the job for that one. My favorite. My result said, I just submitted 40 jobs. And they all came back and said, what's their message? This can't come in the file. Can you tell me what's wrong? Okay. With laws, but really important for us.
Yeah,
because they're frustrated.
We were all there.
They're stressed or they're under pressure in ways where they're not seeing the output. You know.
There's a good way. I mean, I don't know if there's a good way or not. Is there a good way to do that? At least search the tickets to see if the questions that asked before? That's the fundamental thing you do on Stack Overflow before you ask a question, right?
Our tickets are not visible. And I think that's not a decision that's a matter of privacy. That if the questions are visible to the public, people may not ask questions or speak as frank, or that there's a level of visibility that exceeds reasonable privacy expectations. There are forums, and I have to tell you, sometimes we get frustrated in drawing forums, right? But no, they're not. They're not. We think. Now, that does raise interesting questions about there's a recurring problem. Should we make it too available? I work there for.
We are blessed with a cafe, don't we?
Yeah. Well, you're raising good questions. So. Right now, I would like to reduce the incidence of people that submit a ticket on both sides of the same ticket. And I think it's a reasonable thing for people to say, I don't know quite who to ask, whether to ask TACC or C. But I think I'll just ask them both, and that increases the probability of answering the question. And they'll realize it's going to the same.
Yeah.
These are also not standard tags.
date. What time do y'all usually start up in the afternoon? About 1?
Yeah. I guess, did Dean take them? Is that what happened?
Last I saw him, they were with Chris.
Okay. Cool. Yeah, I just want to make sure you're all set up here, and you want to present from your laptop. You know what? We're just not gonna. We're gonna ignore this for now. We already did a session, and that's fine. I'll get you online for the afternoon one. You have this guy, HDMI.
Yeah.
Yes, sir. Pretty simple in terms of setup. So we'll plug this guy in, and your computer automatically does stuff. I think if you look at the back here, you have the lectern HDMI, and you can send it to everything. Boom. Looks like you have an extended desktop.
Yeah, I guess I should get rid of that, huh?
You can probably use it. If you start viewing your slideshow. Oh, you don't. You're using
I'm just gonna get rid of it.
You're using Google. Display.
So with your Fedora, do you not have problems with like Google products?
No, not really. And what do you mean?
Just they suck. They like hang all the time. Like I quit using Google Search. I have to use Gmail, but it's gotten a little bit better. What did I end up having to do? I had to turn off IP6. That seemed to help a lot.
Mm-hmm.
And then I have to keep my cache like cleaned out all the time, or else it just starts to hang.
Really?
Yeah, it's kind of a big pain in the ass, actually.
That does sound like a pain in the ass.
How do I do this here? I want to duplicate.
Clone. How do clones? There you go. Oh, no, you turned it off.
Oh. You like that?
There you go.
I just can't see because they're different sized, I guess.
Right, and I think you can do the, is it this button? Yeah, then drop that guy to
What was it?
what is it, 1280 or something?
1280, 720. 80. Uh-oh.
Of course not.
Let's see what that looks like. Whoa.
Beautiful.
I've done this before. I don't understand why it's
So it's always good to play with it.
not. Maybe up here? It doesn't like that.
So what you can do, I guess, since you have this as an extended monitor, you can just, this is your display, so you can see it here and just progress with the keyboard.
Okay, let me.
Yeah, it's at max. It's HD.
This is weird though. I mean, I know I've.
Yeah, why does that look funny? Let's see here.
I can move this in. Nope.
Oh, can you line them up? Line up the bottom.
That gets me the whole thing at least, right?
It looks like it. Pretty close.
So it looks like.
Maybe do your presentation, see what that looks like.
Not quite.
Oh yeah, actually this, if you look behind you.
Okay, good enough. So, okay, but if I want to now. Okay.
Oh right, but if you actually want
Try
to
this
do
again.
a demo, that's something different.
Yeah. That's a bummer.
No. It's kind of weird that you can't make your laptop a this display turn into 1280 by 720. Auto. So you don't have a. This guy has a graphics card, doesn't it?
Yeah, it's that old integrated stuff. It's weird that that's the only options though for the monitor.
Yeah.
I mean, for the.
Yeah. Was one of the options 640 by 480 on your display?
No, not.
It
Yes.
sure is.
That's gonna be horrible.
That's going to be awesome, isn't it?
Yeah, that's unusable.
Oh, you want to clone them too? Put one on top of the other.
Oh, geez.
Make this guy big again. I don't know, hit enter or something. If you hit Alt space while you're on this guy, Alt and space should grab it, and you can move it with the keyboard. Do it Alt space M. What window manager are you in? Okay, there you go. So if you go back to the 640 option, I know that sucks, but let's just see if we can do this. 640 and 640, and then stack them. Okay, no, it does actually. Yeah, that is the full screen behind you. It just looks it just looks fucked up on the confidence monitor here.
Oh, fuck. How do we get back to that? So good to go. Close.
It's too small for you?
Yeah.
Okay.
All right, they're all experts now on computational fluid dynamics, heat flow,
Excellent.
water flow,
Gallons per minute.
how hot it is in Texas in the summer.
All right.
High humidity.
Excellent.
Okay, getting ready to kick off again, huh?
Yeah.
All right, one more. Enjoyed it. Thank you. Thank you.
Thanks, Chris. And we scheduled the 3:30 with Dan
It's at
and
3:30.
Kelly and you. Yeah.
Okay. Okay.
You're instructing us to see.
Who's David today? What's that?
He said,
Oh. Huh?
he said something you heard when he said, yeah, I don't know. Oh, yours.
Oh.
Yeah, good enough. We'll make it work for now. Maybe play with it more over lunch.
Okay.
Maybe.
You're happy-ish?
I don't have any live demos this time, so
Okay.
let's see if this at least comes up. Okay. More or
Yeah.
less.
See, it looks better there than it does here, too.
Yeah.
It cuts off the bottom.
All good.
All right. Thanks, Dave.
Hey, Mr. Larkin?
Yes.
How about this? You know how it says people are going to watch the webinar thing? How would I do that?
Go to plus, Google Plus.
I'm already on Google.
And then search for Texas Advanced Computing Center. And on the page you'll see on the Texas Advanced Computing Center. Not the one that's actually called.
Yeah, I know what you're talking about.
Yep, it's not TACC though. That's you get the yes, it's that one.
Yeah.
Okay, and then scroll down, you'll see all of those videos.
Oh, you can't like watch them.
You have to lunch, guys.
Yes, you can watch. You can watch them live.
Okay, pizza for lunch.
Yeah.
Rosie, what email?
Oh, what's that?
You can watch them live. Only when they're happening. Yes. He's not going to do. He's not going to present this one. Yeah. Yeah, and then you know the rest of it. For me,
What'd you say, John?
We have a pizza today.
good.
And a group photo.
You show how awesome you are for the website.
No, but that's until 7.
What?
The pizza. Yeah, today. The bowling social.
Oh, I think you're talking about just lunch.
Oh, no, the pizza bowling
And
session is next week.
Yeah.
Yeah.
I believe so.
Oh, never mind that. So.
Yes.
Did you buy it?
What if you buy it?
It's gonna be mostly a lecture, especially right now. Okay. So is this pretty much everybody? Y'all tell me. It looks like it. Most of the seats are full. So okay, cool. So we'll get started so we can get to lunch.
Will you be doing stuff after lunch?
Yes. Yeah. I'll talk about the schedule just a little bit. Keep you guys oriented. Okay, so my name's David Walling. I work basically in Chris's group. It's the data group here at TACC. Kind of done a lot of stuff over the years at TACC. Kind of started out with like building basic business back-end systems, doing web page type stuff. Started back from a master's in statistics in, I guess, last year. So I've been kind of doing that part-time, working at TACC full-time. And so doing more like data analysis, helping our users kind of get their codes up and running on these systems to take advantage of, like, you know, Stampede. Y'all just took a tour of Stampede, right? Right. So, you know, as the data sizes grow, the amount of compute resources you need to analyze that has to grow with it, right? And it can start getting a little complicated. So we'll just start off before lunch here. I'm just going to give you kind of a quick overview of data analytics and kind of the workflows you see there. Then we'll break for lunch, and then we'll come back in the afternoon and we'll have 3 relatively short sessions, but we'll cover ETL processing, which you end up having to do a lot of anytime you're working with data. And it really doesn't matter what field you guys go into or are working on, you're going to have to do this if you're doing any, you know, it doesn't really matter. You don't have to be a computer scientist to have to worry about these type of issues. Then we'll have 2 sessions on 2 very nice tools that I use quite a bit here, Python and R, which I know you guys have probably heard of Python. Who's heard of R? You know, maybe not very many, like 20%. Yeah, so that's pretty typical, really. But I personally love R. It's not just because I'm a statistician, but it's a really good program. You know, I've used a lot of languages. You know, it has some very nice features. So we'll actually dig into some code in these 2 sessions and kind of play around with it. Obviously, I can't teach you how to program in Python or R in, you know, an hour's time, but I hope to expose you to these tools and give you some tips and some pointers to some really good online resources if you want to learn them more. Who's actually does a lot of programming? I'm curious. So again, about 25% maybe? Okay. Y'all use Python?
I know.
Yeah, it seems to be really popular these days. It's really easy to learn, and you know, you can do a lot of things with it. So so when we talk about data analytics, we actually are in a pretty exciting time for science. You know, for thousands of years, you know, we've had people sitting there watching nature essentially and kind of recording what's going on, just kind of describing natural phenomena. You know, that was kind of the first paradigm of scientific research, just writing it down, what's going on. You know, looking through a microscope up at the stars and seeing, okay, this star was here one day, now it's over here, you know, a week later. And then, you know, for about the last, I don't know, 200 to 400 years, some really, really smart people started taking on those observations and actually come up with these very beautiful mathematical property or mathematical models that actually describe exactly how these natural phenomena are going to occur. All that stuff's a little above my head. I'm not a math major, but I can still appreciate how just like elegant and beautiful that actually works out to be. And so that kind of gives you these first principle level models for describing science or for describing natural phenomena. Of course, part of the reason that they're so elegant is because they make a lot of assumptions and they kind of simplify it a little bit to have these nice, succinct equations, right? And as these models start to become more complex, the ability to actually perform those calculations becomes impractical. Well, in steps the computer systems that love doing calculations. They love following rules, which basically is what a mathematical model is, right? So it really allowed, in kind of what you'd call the third paradigm of science, to start exploring these more complex situations and turn all the heavy lifting of doing those calculations over to computers. And so that's kind of been our bread and butter here at TACC, right? Is people come in here with these first principle models. I think I'll talk about this a little more in this lecture, but and they're able to simulate what the system would do based on these mathematical models only. But now we find ourselves in what they call the fourth paradigm of science, where now we're actually starting with data that we're capturing from the environment, that we're capturing from as output of the scientific research, and actually kind of going in reverse, right? So you start out with the data. You don't actually know mathematically how the system works, but you can start to fit different models to it and start to explore it from that standpoint. So that makes things that were previously impossible to tackle, like the body is an incredibly complex system. There are some mathematical models that describe parts of it, but as a whole, it's just way too complex. You almost have to go in reverse and start recording gene expression data and different things about the body, and then you can start making some insight just by fitting statistical models to that. So our bread and butter here at TACC over the years has been this kind of third paradigm where I have first principle models describing the system. I'm going to provide some initial conditions to that system. So at time 0, here's my pressure, here's my temperature, so on and so forth. And those mathematical models are going to spit out exactly what the system should look like at time t+1, at time t+2, right? That's what people traditionally have done here on at TACC. And as our systems have grown more capable and larger, these computationally, you don't have a closed form solution to these mathematical models. All you have are these approximations, and those approximations become more and more accurate as you basically decrease the time scale between each time step, right? So nowadays, these simulations, they output just terabytes and petabytes worth of data, right? So we can do simulations of entire storm systems at a very fine-grained level of our data grid. And so for each time step, each point in that 3D grid is going to have, your pressure data, your temperature data, your wind direction vectors, things like that, right? So tons and tons of data. And at the end of the day, what you usually want to do with that data is you actually want to visualize it, right? And what you're visualizing is the physical properties of the data, right? So here I'm looking at fluid flow over, I think, a submarine fin, right? So you're actually visualizing the direction of the water, the temperature of the water, the pressure in this physical system. So they're all physical characteristics of the world. What we've come to find out is, since all this data is simulated data, is derived from these mathematical models, and there's so much of it, it can actually be cheaper to just throw it away when you're done with it, but keep the code that generated it around so that if somebody else needed to use it, they just rerun the code, get the data back, they can do their research, right? And it just becomes, it's cheaper and often quicker to do that, because even moving the data somewhere because it's so large can take longer than just rerunning it, right? Now contrast that with kind of data-first science, right? So in data-first, you don't necessarily have this model that describes the system. You're trying to find a model that will allow you to describe what you're seeing in the data, right? So now you're talking about things like Dewey, statistical inference, and prediction based on machine learning techniques. And usually this data is coming from things like these measurement devices that are out that are becoming incredibly cheap, and more are being deployed throughout the world. They're coming from things like designed experiments. There's still a lot of survey data out there. We've been collecting that for a long time. And then, of course, just also observational studies. The key point here is that this is all irreplaceable, right? If you lose that data, there's no way to regenerate it because that's what was true at time X, right? And there's no way, we don't have a model to reproduce that. So, and it's usually on the orders, generally when you're working with these data sets, you're still at the order of like kilobytes to maybe gigabytes. Some of the larger, genome type stuff gets up into the terabytes, and some of the social web media can be in the petabytes. But generally speaking, you're still kind of on the lower end of kilobytes to gigabytes. And then the information, the way that you visualize the data is different too, right? You're not necessarily looking at physical properties of the system. You're going to run some like clustering algorithm techniques. So maybe you have, I think this is from a study we did here at TACC quite a while ago now, but basically you have all this email data, and you want to analyze that data and figure out relationships between people in an organization, right? So when you do the visualization, you're kind of trying to tell a story to at least understand the relationships that your predictive algorithm figured out. So there's the president in red. He's really close to a lot of communication goes between him and the director. I think the size is the amount of email, and then the proximity is how. Actually, I forget exactly the size versus proximity, but I think these two like blue dots are like the reception is, so it's clear that they're very connected in some way. And down here, so we're looking at so this is a famous data set that we may play around with if we have time in R. It's plant data where it's looking at petal widths and lengths and the sepal width and lengths, and it's just trying to look for correlation between those two, right? So you would see correlation if the dots happen to kind of line up on a kind of a linear line there, as opposed to something like this where it's more just kind of random, right? So you're just kind of exploring the data, and again, not always tied to a physical property. It's just trying to summarize the data in some way to try to make sense of it. And these two aren't completely, independent, right? So as we collect more and more data, it actually helps us refine our computational models, right? Because now we can run our simulation, and we can compare that to the data that we've collected to see if that simulation is accurate, right? And it may find out that for most cases it is, but you may find these little points in time where something goes wacky in the real data that's not being accounted for by the computational model. So you may go back and start to refine that computational model to account for those type of physical anomalies that you're seeing. So a couple of examples of kind of data-first type research, right? So kind of the big one, and that we're really heavy into here at TACC, is gene sequencing data. So this is an example of a microarray data, and basically what you have here on the columns is different, essentially samples of DNA taken from, say, maybe the first half are going to be from tissue that has tumors in it, right? And the second half without. So each one of those is a different DNA sample, and then each row is basically a different gene that you're looking for on that strand of DNA. And then the lights are how often do you see this particular gene on that particular sample, right? So the green is you see it a lot, black is you don't see it at all, and everything in between. What you can start doing is doing statistical tests such as, okay, for all my genes in group A, the ones that have cancer, is there a difference in the amount of genes that are expressed, or a certain type of gene expression? Is there a difference in that? And is that difference due to just randomness, because we are dealing with samples and we're dealing with things that naturally have some random error in them, or is there a statistically significant difference in those two groups? That allows you to start targeting genes for therapy that may be more active in the tumor cases, etc. Another example would be like in ecological research, so really studying the environment and how it's changing over time, what impacts climate change is having on our environment. It used to be that was a very data-poor field because it was very difficult to attain that data. It's usually somebody going out in the field, sitting there, writing it down in a notebook, going back to the labs. Maybe compiling that into a digital form that somebody else can use, maybe not, right? But as the sensors become cheaper and cheaper, technology just gets better, And not just the sensors themselves getting cheaper, but the ability to retrieve data from them, right? You don't have to physically go out in the field and download the data from the thing anymore. You can just send it through like a peer-to-peer network all the way back to your lab. As that gets cheaper, we get more and more data, so now we have more and more information about how the world actually is at a given time. And you can start doing more advanced analytics of, what is the runoff like in this particular creek? Is it going to, what impact is urban development going to have on this particular ecosystem? Running predictive models of how building a new road is going to, affect the wildlife in this area. And then finally, like the one you see a lot, if you go online and people talk about big data and all this kind of stuff, they're usually talking about like the social data that's being produced. So Twitter feeds, Facebook like data, so on and so forth, right? And usually there you want to analyze things like how do I improve the click-through rate on my website so I make more money off these ads, right? So you're going to get a lot of data based on you're tracking every user that comes to your website. It's just creating a tremendous amount of log data. And now you have to go in there and mine that to try to start answering some of these questions. It's really, there's been a bigger business focus here, and it's kind of led to a lot of growth in the tools that are available for us to use to do that. But there are some basic kind of pure science type questions you might want to ask about that. And for instance, some researchers at UT are doing some pretty interesting things like analyzing Twitter feeds and to try to study how cultures differ, right? So your anthropology type stuff, your sociology. There's a case where a guy's trying to do text mining on books to study like linguistics, essentially. Can I tell geographically where a book is from by the language that's being used in it, right? So some pretty interesting stuff there.
I'm curious. So then they create algorithms from observing people's behavior.
Yes, essentially.
So, like, when they make a formula, like, how is that beneficial? Like, or I guess not getting. You wanted to find out, are these people going to tweet about going shopping today? Do you like make an algorithm for that to predict?
Yeah, well, so there's various different ways, and I'll talk about the difference between statistics and machine learning. They're very similar, but essentially that's something where you would have like there's various different algorithms you can use in machine learning. Essentially, what you're doing is looking for patterns. So, and it's usually supervised learning. So you know from the past that people that had this pattern in their data were likely to go buy this particular type of shoe, right? So it's trying to find those patterns that would predict when they're going to do that.
Oh, it's like those Facebook things that they recommend you.
Yeah, I mean they're huge. Yeah, there's a lot of, and some of these, and I'll talk about this a bit. A lot of the algorithms are kind of black box. Like you don't really understand why they work, but you also don't care because they do. At least judging by your performance of does it accurately predict a user's behavior, right? So it's a very deep topic, obviously. There's a lot of different algorithms that do that, but fundamentally they're just looking for patterns, and they're able to see if that was a pattern of interest because they have test data or training data that says what the outcome was, right? So what does a typical kind of workflow look like in all this, right? So generally you start out with a research question. That's not necessarily the case. You might just have a general thing you want to go start exploring without a specific hypothesis in place yet. But usually the first thing you have to do, of course, is, well, what data do I have available to me? Where can I go and find data? Google's your friend there, of course. Unfortunately, there's still not just a ton of open, easily accessible data sets out there. It's getting better, but just finding what data you need can often be pretty difficult. As you become more specialized in your field, of course, you're going to, just through interactions with colleagues, you're going to kind of know what data you want, but it can still be a challenge. Even after you get that data, and kind of going back to that video we watched this morning, often it's very difficult to understand exactly what that data is, right? So you have to kind of do this first exploration phase where, okay, what the hell do I actually have here, right? And that can be a pretty challenging task. Even once you understand what you have, there's going to be problems with the data, right? There's going to be missing values for certain fields. There's going to be values for fields that don't make any sense, given the logic that is kind of underlying the data. So you're going to have to do a lot of cleaning. And those three fields right there can often take up 80% of the time that you're on your research project. I mean, it's just kind of a rule of thumb that seems to consistently be true for these type of projects. And there's no way of really getting around it. And so this afternoon in our ETL session, we're going to specifically look at tools that help us kind of accomplish these cleaning, understanding type tasks. So once you do actually have some data you can start using, then generally you kind of want to do it kind of in a second exploration phase, right? Like, okay, let's just start kind of playing with the data, see what kind of patterns I can see just visually by doing simple histograms, things like that. You know, kind of start looking at it, and then start refining your research questions so you can perform specific analytic techniques to it. Do I need to fit a linear regression model, a logistic regression model? Do I want to do a machine learning type algorithm to try to predict click-through rate, etc.? And then visualization, of course, plays a key role both in validating your analytics and also sharing the results with others, which generally in science would be through reports and attending conferences and whatnot. So what do data sources typically look like? Or where is this data coming from? And this is by no means an exhaustive list, but kind of traditionally a lot of the data has come through kind of very specifically designed experiments. So I have 3 levels of irrigation amount and 3 types of, or 3 levels of nitrogen that I want to test out and find which combination gives me the most increase in crop yield, for corn or something, right? So I'm going to set up a very specific experiment to test that, collect the crop yield data at the end of it, and then run some statistical models to find if there was actually a difference between the different treatment groups. We've been doing surveys for a long time. Survey data can be very difficult to work with because it highly depends on how the survey was actually executed. I mean, that's a very specific statistically type problem you deal with, but there's a lot of survey data out there. It may or may not be useful. But everybody's familiar with this type of data. Increasingly, we have data that's coming from measurement devices, right? So we have all these ocean buoys out there measuring, temperature, things like that. Everybody's familiar with weather balloons. Tons of satellite data, usually collected by government agency, but generally made available to researchers free of charge. And then, of course, in the last 20 years, really 10, we've seen an explosion of kind of machine-generated data. So it's really all these log files that I've been talking about. So some of these big companies, Twitter, Facebook, Google, everybody, they basically log everything that happens in their data center and store it. Because they don't know what's going to be valuable to them 5, 10 years down the road, right? They may be able to go back and build a product based on all that log data later on. So if they don't keep it now, then of course they won't have that opportunity. And generally speaking, in practice, you're going to, you may set up scripts to pull your own data. We do that a lot here, work with researchers to set up those type of ETL processing systems, but a lot of times you're just going to be getting it from a third party, such as the National Oceanographic, blah, 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 something, weather service. And more often than not, it's going to be sitting out on some researcher's FTP server, and they're just going to may or may not let you go connect to that FTP server and download the data. Typically, the type of format you're going to see is, by and large, it's going to be some type of text / semi-structured data, whether that's Excel, HTML. So if you're doing like web scraping, the data's there, it's in a semi-structured manner, and there's tools for turning that HTML into valid XML and then extracting it with things like XPath to get at the data. We'll actually look at an example of that later today. A lot of, again, log file data, so there is some structure to the log files. For instance, every line basically is recording an event. It's usually, you can break up a certain type of line, and it's going to be consistent across those type of events, so you can extract information that way. JSON's kind of the same way. It's just nested key-value pairs. Doesn't necessarily conform to some rigid schema, but you can usually traverse it in some kind of structured way to get at the data you want. But there's also just completely free-form text, right? So email data, like a big collection of email or discussion forum posts, right? There's still a lot of useful information in there, but it's more difficult to get at because you don't have any fixed structure to actually look at it, right? You have to do other things. One that we see a lot here is like field notes. So archaeologists that go out and record information about a site, they usually just write it down on a piece of paper. Maybe that gets turned into digital text or something with OCR but generally speaking, it's pretty much free form. If you're lucky, there's going to be a REST API. Are you all familiar with like REST web services? Right. So you go to something like this, right? So I go to a URL. It's going to hit a web server. It's going to return HTML to me. A REST web service is kind of the same concept, except for now when I type in this URL, it goes to the server. I can pass in things at the end of the URL that are basically parameters, and it'll process that request and now return to me JSON. So it's returning me data, not necessarily a web page I want to look at, right? So that's basically the concept there. These are becoming more and more ubiquitous, and data is being made available through these more and more often, and they're actually very easy to work with. So hopefully your data has an API in front of it. Probably second to kind of the text semi-structured CSV type files is maybe they'll give you either a dump of a database or direct access to run queries against a database. And generally that's good, but it doesn't necessarily mean just because it's in a database that it's not going to have a lot of the problems. A lot of people, especially in like academia, don't have a lot of formal database training. So basically they take a CSV file, stick it in a table in a database, and that's it. They don't use any of the power of the database to ensure that the data is actually clean and it can't be messed up through things like constraints and proper normalization of the data. But at the very least, it allows you to write custom queries to pull out exactly the data that you want. And then sometimes you end up with proprietary or binary data, which if you happen to know the program that created it, you're in luck, and that program's still available, then you can maybe extract data from that. I think they touched on that in the video earlier. This is maybe less of a problem with data being generated today. There's much more standards out there, but especially if you wanted to look at some data from 15 years ago, there's a good chance it's going to be in some format that you just can't access. Just a bunch of zeros and ones. It doesn't make any sense unless you have the original program that created it. So once you do have your data, you find out what data you want, you know what format it's in, you can start to explore it. So you start asking questions like, okay, exactly what do I have? What does this column name actually mean, SAM1 versus SAM2? That doesn't really make any sense to me, right? I see something that looks like a timestamp, but I have no idea if that's in Universal Standard Time, or if it's Central Daylight Time, or if it's just Central Time. Those are all different. You may have to, so say that data, there's different techniques. If you can't just ask someone, because usually the metadata, what they mean, is stuck inside the researcher's head, and that's the only place it exists. So if you can't get it directly from them, you might have some options of running some simple analysis, right, to try to figure this out. So if I have timestamp data that I know is supposed to be from Austin, and it's recording temperature throughout the day, right? If I start plotting that data and see that it's showing me that, and I'm assuming like UTC, right, or Central Time, and I see that the hottest part of the day is 11 a.m., then I probably know, oh, actually, this is actually UTC data, and so I know how to convert it, right? It gets even trickier when, well, is it Central Time or is it Central Daylight Time? Because then the only difference is going to become at twice a year when the time changes. So you're going to have to like zoom in on the data at that particular point and try to make an informed guess of what it actually is. You probably use the same type of logic to figure out things like, well, is this kilometers per hour or miles per hour, pounds or kilograms? You kind of look at the data and like, does it make sense that this person's the average weight of these people is 350 pounds? Probably not, so maybe it's kilograms. You're going to see a lot of special codes in data. You'll see negative 9999. Well, what does that mean? Means it's basically a null value, it's a missing value, or is there actually some other, is that tied to a special code somewhere in a README file? Who knows? Generally speaking, the best case, you're going to have this type of README file that explains some or most of these columns. More often than not, you don't even have that. Unfortunately, that's just the sad state of things. But assuming you can answer enough of these questions to start using the data, then typically you have to perform some cleaning or some transformation of that data, right? So here's a particular field. It's heights of basketball players, right? So 5'11". Well, I actually need to transform that into inches because it's hard for me to input 5'11" into some kind of a model that's expecting a numeric value. I know that this field, these string values in my data map to particular database columns in my research database. So I need to do a mapping, transform that string into primary key in my database. I know that if I take these two fields and combine them, that actually gives me a unique key for this particular data set. Each field by itself does not. And I need this data to be stuck in this particular database or dumped into a CSV file that looks like this, which my analytic program is expecting to consume from, right? So more often than not, this involves extensive scripting. Again, their first session after lunch, we'll kind of look at how we actually go about doing these type of things. But once I have the data cleaned up in a format that I can use, again, there's usually a second kind of phase of exploration. So you start looking at things like summary statistics. Usually the first thing you do, that doesn't really show up very well, but almost always the first thing you want to do is plot a histogram of the data. You know, just get a feel for what's the distribution of my data. You can start implementing some simple pattern searching, doing basic info viz. You know, if I think that my data follows a normal distribution, I can plot a quantile plot to see how well that actually matches. And you're not necessarily at this point asking any specific research question. You're just trying to get familiar with your data so you can know what questions you can ask of it. And that leads you into the actual hardcore kind of analysis, right? And usually this takes two approaches, either kind of doing statistical-based analysis, so kind of fundamentally, without going too in depth on this, you have this entire population, so all the people in the U.S., and you want to make some kind of inference about them. You know, what's their mean income, you know, so on and so forth. But for whatever constraints, usually it's money. I can't collect data about every single one of them, so I only have a relatively small sample, right? So based on that sample, I want to still say something about the entire population. So that's the kind of fundamentals of what statistics is all about. So now you can start applying different models. You have parametric versus non-parametric. The former is you assume that the data is coming from a known distribution, a normal distribution, Poisson, so on and so forth. You make your inferences based on that. Non-parametric would be you don't assume a given distribution, and you just use other different techniques to actually come to similar conclusions. You may apply linear or logistic regression techniques to it, and fundamentally you're doing hypothesis testing, right? So I have this treatment X. I want to see if it improves life expectancy. So my null hypothesis is it doesn't. The alternative hypothesis is it does. I analyze the data. I see that there is a difference in the mean life expectancy, but is it statistically significant? Is that difference just by chance, or is it more likely to come from some fundamental treatment effect of treatment X? And then you have code out there and programs that help you do this, so you can run a Shapiro-Wilks test to see if your data from your linear models actually is normally distributed, which is one of the assumptions of doing linear regression. You can actually run your linear model, get the output, see that yes, in fact, this particular variable is statistically significant and has some impact on my study. Kind of the other side of the coin is what's machine learning. And to be honest, it really is just statistics, but with sex appeal. It's kind of what you're going to make a lot more money doing machine learning than you are statistics right now, even though fundamentally they're the same thing, right? They just have different terms for the same kind of stuff. So in statistics, I talk about my parameters. Machine learning, I'm talking about explanatory variable weights. You know, I'm fitting a model versus doing supervised learning. I have my statistical model versus I have some neural net graph that I can run my data through to get my prediction out of. And also, you're generally more worried about performance in machine learning, which performance is usually defined by prediction accuracy. I won't get into the difference between prediction versus inference, but generally prediction, your confidence is going to be wider than your inference-based confidence intervals, because you're trying to say something about the next value you see as opposed to the average of 95% of the data or something. Maybe this isn't a completely true statement, but generally speaking, machine learning comes more from the computer science side of things. It's more algorithmic based than it is like fundamental statistical theory behind it. And again, they're okay with black box solutions. They don't have to. Where a statistician wants to dig and spend years studying exactly why some model works, they just want to come up with an algorithm that does better than the algorithm they already have as far as predicting whatever they're interested in, right? And then finally, after you've run your analytics, you're going to use visualization mainly for two purposes. One, you're going to do validity checks on your model. So this is I'm running a linear model. I have to check some of my assumptions, so I have to see that my residuals, which I guess we won't get too into too much detail what that is, but it's the difference between the actual values and the line that I fit to the values would be like your residuals. You want those to be randomly distributed. You want, you want those to be random. You want them to be normally distributed, and some other specifics that are very much tied to that particular analytic technique you use. So you can use visualization to kind of see how far off from those assumptions are you. In a lot of cases, these methods are robust to being not perfectly normal, not perfectly random, but you want to get some idea of how off it really is. And then, of course, you want to tell stories with your data, right? So there's a lot of different techniques too. And I just kind of stole these from the web, but there's this technique which I've seen used quite a bit here at TACC, which is you have this big collection of data. You want to easily break it down so people can see like what proportion goes with which group. So one of the more interesting ones I've seen, I think, was on data.gov, where they broke down like the U.S. budget using this kind of tree map type of view, so you can see, oh, this would be all of. That's not exactly what this one is, but like this would be the entire defense budget, and then you can break it down into Department of Navy, Department of Air Force, blah blah blah. Right? Just allows you to easily distill all that information out into a relatively easy to consume plot. This one is the result of like a k-means clustering type algorithm. So I'm going to highlight the clusters I discovered in different colors, just make it a little easier to for the audience to see, right? And with that, so this afternoon, again, we'll come back. We'll spend some time looking at how you actually deal with this acquisition, figuring out what you have, cleaning it up, putting it somewhere that you can now use. And then we'll do 2 sessions, one on Python and one on R. It's really just to expose you guys to these tools that haven't been exposed to it, and hopefully motivate you to go and learn more about them after this class is over. So with that, I think we have lunch, and I believe John said we'll be back at like 1 o'clock. I heard pizza was coming. Is that true? I'm cool with that. And all right, thanks, guys.
Thank you. Yeah, so I was expecting to get shut.
It's actually kind of, so I started working as an intern. I just kind of found out about TACC.
Yeah, no,
I worked as a library. Actually, having to be somebody I was working with. I found out about TACC. Basically, I was kind of begged to people here for the got that job.
If you can do something,
You said you're a senior?
Yeah. So
well, I should have been like, don't touch me. You know what I mean? Like, you touch me like real quick. I didn't have
What's your focus then? Well, if you're interested in tech, we're always hiring. Obviously, so this is all you guys are in part of you. So you have like a project planned out for the next. Yeah. So that's kind of how I started working. Yeah, basically, got involved in that. Undergraduate, just came up with yeah, just do a really great job in the R&D part. Like I said, we're usually hiring on generally speaking, we have several. Yeah. What is your R&D project?
Well, she hasn't really given her illustration, but we're working with her doctor.
She actually just sent us an email.
Oh, she just sent us an email.
course, it's just a folder. So
Yeah, the salsa, I'm still on it. But I still have a chicken. Oh, you're right. It should be just like oh, she's so sweet. She had her personal friend. I just did.
yeah. Yeah, I should be able to. I can probably upload almost all the stuff you class. Maybe the third version of it.
For 6 and 8 hours. So that's fine. I probably won't, obviously, because it's so productive. That's also
Yeah.
just because. For some reason, I can't accept the invite. Maybe AOL doesn't.
That's just, I think, the name of this. I was looking at what I'm doing because my mentor sent me. And there's non-uniform national.
Oh.
It has to do with 3D geometry. I guess it's basic.
I hate the word geek. Like, I don't ever want to be called a geek. I don't know. It's just.
Does anyone actually ever use those words?
Yeah.
Like, you're such a weird name. Like, who actually does
Yeah. I think it's memorization style now.
Actually,
my friends are like,
it's
I'm
more,
totally
it's
doing
more
it.
like,
I won't see it and today,
Yeah.
and I'm just like,
it's actually fun.
guy.
I was gonna say nerd is the
Yeah.
oh, I mean Jackson.
Yeah, we're
Yeah, it's become a style, and then a lot of my friends like they'll play like one video game that we play that. Like yeah, they're like, yeah, it's really exciting. And it's just that's just like.
You don't know
Like I used to have kids on it, you call it, and now everyone's trying to do like this stuff like that.
Yes, people global people probably
What was the name of that student on that? Why would people buy electrical cars we can charge it for 6 to 8 hours and then only working on one day.
Well, most of them are like.
Or sit here and you still not have that time.
Yeah, like in major cities, like, you know, I've never done that. I would make these.
Honestly, there's
I mean, but most people
very
can
intense.
try.
Like some of them.
Right, I mean, if you're gonna look at very, because of the size and just the populations, long range computation. Austin, like, didn't have we have to like, oh, I have to charge it with all of that.
Or like those like smart car things. No, like the cars you can just pick up anywhere and drive.
Well, never working for them is great salary, so I would just want to last more. So I don't know. That was stupid. I'm not gonna say that. Like when the guy was like explaining to me, I was like, so he was like, yeah, like you can charge your car at like Whole Foods or something. I was like, oh, like while you like shop. I was like, oh, how long does it take to get a full charge? Like 2 hours? And he was like, yeah, 6 to 8 hours. And I was like,
Yes.
So you just charge it like every night, you know?
yeah.
Or like I saw that they have charging stations here.
Yeah, they do.
So you just like drive to work, charge it, go home, charge it.
I know there's an idea right now that it's electric cars are being where everybody them they would put charging stations like individually. So when you go past the like they would charge your car.
Yeah, that's what he was telling me. He was like, they would get better. It's like for people.
Right.
Right now, they're more
I don't know what you're talking about 80 miles, so like I just canceled the Tesla, so it's like.
No, I told the guy who I talked to at the Austin corner, like, because if you look at he works for Tesla.
Well, I mean, like Tesla says on their website that like with the battery, if you driving highways 65 miles per hour.
Is that objective as far as I understand?
They just came out with that new car that people.
Wait, you mean their speed?
What?
No, I'm not talking about their speed. I'm talking about how much.
Or they
The
charge.
miles, like how many miles you can go on the track.
Yeah.
It says 261, it's like 65. That's a whole lot better.
Really? You told me
I mean,
about
this
it.
is like
The normal one.
oh, never mind.
But it could be the latest model. Have you ever worked in like? I thought he was interesting, but maybe he doesn't want to work as a
No, she has everything.
No.
I didn't know. Oh my god. Computation. I can't not spell computation.
No, this is my thing. I don't remember.
Yeah, they have a first for out.
So you want these on the side?
I would never take someone else to have this.
I think that's just check stuff.
Oh, not
I don't know when she started, but obviously she doesn't have like a like I heard it's happening in class. She just finished it. Look, I don't care how old she is.
Hey, you always hungry or what? Oh, yeah.
Yeah, I know, really. Yeah, no one's like a picture.
And then ask.
Oh, your phone?
To the Tesla? Oh, yeah, I save money on it.
Can you say from both?
Huh?
Can you say from both so she can say one email? We could be like saying thank you.
Yeah.
Me, from me, and so.
Oh, for that one?
Yeah.
Oh, okay, yeah, I can tell. This one is for the guy I met at Austin. I don't even care. Like, the minute I heard this is like, people all the time. Sometimes they'll have the salary start. Once I did that. Thank you so much for. I'll go on I am.
Oh, you don't want to see the green card? Right, I lost this whole Are you finished what I'm watching right now?
It's so good. I watched it in 2 sittings.
No, probably.
I know, bro. I did the same thing. Yeah.
If a person that you meet gives you their phone number, like, does that mean you're supposed to text them? Yes.
Oh, she said 600. She wanted that to help with it.
Okay, so then I get them back to okay, but I'll come back on that.
What? I don't know. All right.
Currently, my family is financially challenged and it's very hard for a TV show at this time. So this matter,
Roger.
oh, yeah.
This came.
Oh, I guess it's back.
You move so fast.
Oh, shoot, that should go over a meeting on that.
Oh.
Yeah.
Apparently, there's a couple of clouds, and a half of clouds. So, before the doctor cut. He was pretty much in the service. And I don't think he had it. Scott and Scott. I don't know what you- That's what I'm saying. Probably magic.
Why?
That's why I stick to it.
They hate the dry ass
Huh?
Oh, he hasn't contacted me.
I love it. It's like glass door. I can look at inside. Anybody want any Dijon sauce? Dijon sauce.
That's good, thank you.
Where'd you get that from? Is that what you brought?
Yeah, I bought it from Walmart. No, HEB, sorry.
Yeah. Actually.
They have so much.
Really? I know.
Because that's what they are.
Hell no.
Holy shit. What?
This is crazy.
This is insane.
Yeah, maybe.
Have you seen the movie?
Now, what is it?
What's it about? About basically how Coke can get to American.
What are you watching?
Hello?
How we trying to?
You guys, they pay so well.
Was that Johnny Depp?
Yeah.
Yeah.
Have you seen it?
That's a good movie.
How much?
The average salary is $7. Oh wow. And popular research is so associated with So anyone looking for a job?
What?
Oh.
That's
I'm looking for a job. A job.
You
The lowest is 42,000.
That's probably
like people who work.
Yeah, that's not just the people who work in the office.
Anyone else play Clash of
Oh, I
Clans?
found his salary.
Anyone else play Clash of Clans?
I'm sorry.
Seen the commercial, the projects all of the skeleton.
Oh, you watching it? That's not bad at all.
yeah, but like then also have to get the job in the first place.
I don't think it's a job right now.
What was the name of this guy we were talking to? So you don't think
It tells you their tape.
Yeah, that's all public information.
How much is locking there?
Yeah, you can Google it.
62.
Not bad.
Not bad at all. Hold on, I just saw Kai whatever. He was like in
Can you see everyone's tape?
Yeah, you can see everyone.
All Texas State employees.
Dang, you know what? You guys.
God damn.
Oh my God, don't.
Man, it's a
The guy who taught us yesterday,
Like,
last time, he used 125 a year.
Texas what?
Yeah, I think so. He looks like he makes a lot of sense. And
You just type in a name or what?
You just type, I actually go like to the advanced.
She said, I am so.
I was just curious.
I'm a curious person.
Who's the
Until.
like this salary?
Alright, I'm right off of it. Well, hell, look at that.
Are you looking at it right now? Why?
Bro, what the hell is this?
What are you looking at? I'm like a drama. You're just watching the grappling. Because I do not want to watch.
This bitch ass nigga.
I do not want to watch.
Damn.
Oh, what was the name of that access?
me.
I think they want to hear that. They're gonna be like, well, of course you need money, because that's what you're. I don't know. I was trying to make things so more like intelligent and like right. Get impressed. Or like you're thinking you're feeling. Sounds smarter than you sound. You can be
It just sounds smarter than you sound.
smarter than you sound. Like you're going to do something. Words are there. It's smart unnecessarily. Didn't you direct yourself to the north? You will find the position of, you know, I mean, it's just overcomplicated. I'm not overcomplicated, but I'm just using smart. He was like, oh, yeah, you guys learned about that. And it's like, let me break it up into small parts. I was like, oh, we were talking about when he said partition. I was like, force. Force.
Hell no. This is the most effective system. I don't know what you were expecting.
I know. You expected the baby made a watermelon? I don't know. I'm surprised they didn't give you a blossom.
My department that just figured out to get me out of this.
I can't imagine someone that really had it for its fullness and they just ate a watermelon.
I just feel like it's scary what they did. Waited.
But that's exactly what they do. I really hope this is somehow. Inside of the watermelon. And I feel like it's twin, but it looks both of them. What is that?
Halloween.
That's very creative.
How would you ask the police?
I think it's a wonderful holiday. I mean, I would ask if it was like a comfortable for an adult, but
I think it's the only thing you're gonna pay in school. No, it's a very large one. I have a baby in the watermelon.
So, folder that she has online. About chemistry stuff on it. That she actually uploaded like a week ago. I'm gonna tell you right now, it's a little dense, but as long as it can go through, I'm saying.
It's supposed to be the
I was wondering if that was like, whether you have to
No.
ask for information, so I thought it was like flash and just happen to like,
So should I read like the summary?
no, I mean, I'll definitely read through it, but the second you start, like, there's all in hand.
Like skim through it?
Yeah.
This is a 200-page handbook.
Oh, really? This guy right here.
Oh my god, I don't think I want to. And she was like, don't be overwhelmed.
Yeah, no, I mean, I've had to use that for like 3 years now. I'm sorry, like 3 years class. It's just, it's a lot more information than what you actually need. So whenever like they, they'll each paragraph, it has like a picture point to it. So once you get that picture point, there's a little bit of font. You're good. If they like want something like that,
Oh, I got
yeah, no, don't pay too much attention to that. But the book, even like without that, the book is still like pretty insightful. Like a lot. But you'll definitely get to see yeah.
But there are some people. I thought it would be.
This name can
It's just so crazy.
Yeah, she actually attached a message to it. She wants us to look at chapters 5 and 6. And she said that the descriptions are pretty extensive, so you're going to be good.
I'm very thank you. I feel like there's so many some professional.
Watch you get tracking.
Tracking what?
No, like one of those. Very large.
How do we get the movie?
Inside a Pokeball. You did not look that.
Oh, I remember that old show.
That was funny.
Oh, yeah, I remember this one.
Yeah.
Six gravity. It's like a statistical. Pretty funny. It's stupid. And no, it's like a joke. I understand size higher. I don't like you'll have to use it. Eventually you'll get to maybe like temperature. I can understand it. That's what I read. It's just like in the data type temperature. You want to read anti-temperature. I just can't. It's great. Okay. What? You have to read that. You have to read that. We have to remember the fact that we get no idea. It's like, no, it's not. Oh, it wasn't. That was like, what the heck?
he's saying. I can't understand.
How did he not die happy for that?
Bless you.
That's hilarious.
He was trying to work but you don't have to do part. I got part band and decided he did that. He tried to software and gas instead. And it killed it. Just really like outside.
Arnold. Arnold. What did you have to search to find this picture? Like, really?
Yeah.
First, you was a baby.
Yeah. There's a computer with somebody else sitting in front of it.
Hey, we put to take a picture of you guys. Would you mind stepping out in the hall so I could do it in front of the supercomputer versus in this super beautiful room? A picture.
Oh. No. I don't know.
Ugh, this sucks.
Bless you. What? What was in the search bar?
Like, when people are creating like their babies to show straight out, like, they look like it's all the work.
So you didn't turn your alarm on? So that's not what you were looking for. Arnold. That one was not relevant.
The world is not very short.
Why would you read this? What the? No, right now. Wow. You really gotta read that.
What's the last part? I don't understand the last part.
I don't know.
What's going on with the last part?
Nobody's there, right? It's empty seat.
She was here, I don't know if she got the right one.
One more back there.
Yeah, I don't know where everyone went.
I mean,
It's her bag.
Give it a couple minutes.
I mean, I got
A lot of y'all are from out of town, right? Let's see. Yeah? Y'all sticking around Austin this weekend? Doing any X Games or anything?
Oh, man.
It's in Austin this weekend. Starts today, I think. You know, ESPN.
It's like down there. I was anonymous and then.
Oh, Riley Bond is coming out. 20 months.
Yeah.
He's a skateboarder?
Yeah.
That would suck.
Big shoes.
Kind of like a Will Smith son.
Oh, yeah. Wait, what's his son?
I think it sounds like.
Wait, what's his son?
Jaden's Yeah, no, what? Oh, me, I think no, not no. Yeah, when he, I'm thinking of iRobot.
Yeah, okay.
Is iRobot? iRobot.
I am Legends, like.
Wasn't too bad. I mean, I never saw that movie with it.
After Earth, is that what you're talking about? I heard it sucks. Let's go ahead and get rolling, because as soon as we get through all this, we all get to leave. So we're going to cover 3 pretty quick sessions this afternoon. I'm going to start off by talking about ETL and the tools that are out there, the tools that I use a lot here at TACC. We're going to do a session on Python, where we're just going to go through, kind of look at some basic coding in Python, and present that through a pseudo GUI called IPython Notebook. Then we're going to finish up looking at R, which is lately my personal favorite language. I do a lot of work in it on a daily basis, and I'll kind of, there will be some slides, but I'm hoping at the end we can just kind of play around with some stuff. And actually, you guys can see some R code and see what's possible. So, so kicking things off. So ETL processing. So basically, the motivation is you have all this data out there somewhere that you need to use for your research. It's going to be in various different formats, located at various locations, and you need to pull it all into a single place so you can actually work with it. And so this process is known in the industry as ETL processing. It really comes more from probably the business side, I think, is where this term was coined, when you're trying to collect data from all your different departments, put it into a big operational data warehouse so you can do some business reporting and analytics against your data. But it basically applies to academic research nowadays as well, because everything is basically digital data. So extract is basically what it sounds like. You're going to have some external source of your data. A lot of times it'll be a CSV or databases. It's possible that you can just go out there and scrape web pages for the data that you want. Again, free text, which is harder to deal with. In any case, it's out there somewhere. It's extremely messy. It's almost always the case. And that understanding that data and cleaning it is very hard. So again, this can be like 80% of the actual effort. The cost of the project is going to be paying somebody to do this, essentially. So you need to extract data from those sources. More than likely, you're going to need to transform that data in some way. So this could be things like, okay, in my source data, I have this TACC string field, and I need to map that to my database where I have a table of all states, right? And that needs to map to the primary key 9 in my database, right? I'm going to transform from text into this basically integer in my database. So again, you need to, here's the example of, I have data on heights of basketball players, right? So I have 5 foot, 10 inches. That's a string. To actually work with that in numeric sense, I need to convert that into an integer representation. So I'm going to use inches. I need to convert that to 70. There are cases where people use all different kinds of codes for basically missing values. Sometimes it's just a blank. Sometimes they have these special codes like 9999 or -1, whatever. You need to essentially normalize all those to kind of a standard value. And I use NA here because that's actually a first-class data type, like in a program like R, that just represents this data is missing. Not all languages have that type of support, but the concept is universal. So after I perform these type of transformations, there's a lot of other things here too, right? You may actually do some calculations based on the data and transform it in that way, create new derivative data sets out of it. But eventually you're going to need to then load that into another format that you can then use to go do your analysis, right? So a lot of times this will be a database. Sometimes it's easier just to dump it into like a CSV file, or did y'all talk about a Hadoop file system if you're at that scale? HDF5. Did y'all talk about that in the earlier lectures? So it's like a very common, it's kind of self-describing high-performant CSV file, essentially, that a lot of people use on our resources. So again, start with your source data, clean it up, dump it somewhere that you can access it on a regular basis. And so how do you go about actually doing this, right? Well, usually you start off by just grabbing the data and kind of manually starting to manipulate it, right? And for a lot of people, that's the extent of their skills that they have, right? So that's all they can do, and that'll work up to a point. And I love this slide from one of our, I don't know if they actually created this or just found this on the internet, but basically it kind of works like this, right? It's a trade-off between how easy it is to do and what skills you need versus how much time it actually takes you. So usually the geek and non-geek both start off by just kind of playing with the data manually, right? Kind of looking through the file, kind of figuring out what fields might have missing values, etc., right? So as you get up to this point, the geek starts to get annoyed, so he kind of spends a fair amount of time after actually scripting all this up in his favorite language, right? That takes a little while. In the meantime, the non-geeks, being able to analyze the data keeps going, able to make some progress. But as soon as the geek gets the script done, now he has to invest no more time in that, right? So now he can go straight to just doing the analysis, and he never has to worry about that part again. So if you don't take anything else away from this, remember this, right? It's worth the effort to go ahead and not only develop the skills if you don't have them, if you feel that you are going to need to do this, but to take the time to actually script all this up. And at that point, you have several different options, right? So at your basic level, you have just your basic Unix tools, which I think y'all covered some of these in earlier sessions, but you basically, Linux or Unix programs that you'd run from the command line have this philosophy governing them. They do one or two things very, very well, right? So usually it takes several of them to actually accomplish your task, but they have the ability to simply pipe the outputs of one program to the inputs of another. And essentially, you can kind of glue all these together to accomplish what you want to do. And a lot of old-timers, this is how they would do it, right? Because these actually are pretty powerful tools, and we'll look at a couple of them. And you can make it work that way. So some examples are grep, so looking through files for certain patterns. Awk-and-Said, which we'll talk about in a little bit more detail, and kind of give you my input on how I use these or my opinion of them. kind of moving up from there is using like a higher level scripting language. So the most common probably the most common for this are going to be Python and Perl, but also R is pretty good at doing this, and we'll actually look at some kind of ETL processing in R. Essentially, that gets you into one environment where you could be using a bunch of third-party packages or just features of that particular language to pull in data, do these type of transformations on the data, and then dumping it back out, all within the kind of the Python environment or the Perl environment, etc. So if you're a programmer, this is probably, if you're a software developer, CS guy, this is probably what you're going to want to use, just because you have a lot more flexibility there, and you're already probably comfortable in those environments. If you've never actually done any of this before, you may actually want to use one of these GUI tools out there. So you can basically graphically build up these pipelines using kind of a drag and drop of kind of pre-built tasks for you, and you link them together. I'm kind of an anomaly in that I actually still prefer GUIs over just doing all the basic scripting stuff. I feel that it saves me time, and we'll actually look at it, and I don't know, there's just something about having that visual representation of my workflow that I really like to have. There's a couple of options out there. SSIS is part of the Microsoft SQL Server stack. This is one of the first projects I worked on when I was here at TACC, doing all of our accounting systems, of user time on our systems. It's all a C# .NET based solution, and they're actually really nice tools. The problem is that, of course, they're not free, right? In fact, they're quite expensive. Another one that's really popular in industry is Informatica. Never actually used it. It's supposed to be really great, but again, it's because it's great, it's really expensive. The one I've been using in the last couple of years is Pentaho Kettle, which I think it's very, very similar to SSIS. The greatest thing about it, of course, is it's open source, completely free, Java-based solution. And so we're actually going to look at some scripts that I've written in Pentaho to give you guys a better idea of what that actually looks like. I'm sorry? Free, yes. Yeah. They actually have a commercial version, but that's how most open source stuff is. You pay for support or to get the latest and greatest supported features. But so as an example, here's a little bit of data I just kind of threw together. This is fake data, but it kind of highlights a lot of the common things you're going to have to deal with when doing ETL processing. So basically, we have a CSV file of basketball players, just kind of a random ID, their height, weight, position, and a scout grade for that player, right? So we just using cat to output the contents of this file, which we can do because there's only 10 entries. Generally, you can't just cat something because there's going to be 500,000 entries in that file, right? But we can usually say, okay, well, this one seems to have some missing value for height. This guy has a grade of 6, and really the grade's only supposed to go up to 5. So we're going to have to deal with those type of issues. Also, again, I want to take this height information and turn it into inches so I can more easily process it. So, I could do this strictly from the Unix command line, right? So you pipe together these little programs. They're all based on accepting data from standard in, spitting data to standard out, which I'm pretty sure you guys covered in your bash lectures. And these, again, you glue a bunch of these together, it becomes really powerful. They're actually generally pretty efficient. They've been around a long time and constantly refined to be extremely efficient. The problem I find with them is they can be, even though they do things pretty simply, they all do things different. So they have different parameters you pass to them, etc. And it's just hard to remember all of them. When you have to know 10 different tools to get the job done, unless that's all you had for 10 to 15 years and that you learned them really well, then nowadays it's just, I don't know. They've been they're a bit obsolete compared to using something like Python and Perl or something. Certain folks would kill me if I said that, but they're also just harder to read. I mean, it's a whole bunch of things piped together without any kind of documentation around it, and it's just very difficult. Of course, your command -- help is a lot of help. So when you don't have to memorize this stuff as long as you know how to get at the information you need when you need to use them. Yeah, you should be okay. There are, of course, a couple of ones that anytime you're working on Linux systems, you're going to be using a lot, so it's worth getting pretty comfortable with them. So one of those is grep. We use this all the time. Basically, did y'all do grep at all in the bash? Right. So you kind of know how it works. I need to go find files with this data in it, right? Of course, that pretty much restricts you to non-binary files, but most data you're going to work with is going to be like ASCII text, right? So just go find all files in this pattern, either return me the lines from those files or just return me the file names from them so that I can then go do something with those files. Find is a very helpful one. It's basically, say I'm building a program, it says I can't find some SO file. Well, I can use find to see exactly where that SO file, that shared object file is, and figure out what's going on there. Cat, again, easy to spit out small information on a small file so that you don't have to open the data in a program, look at it there, close the program. It's just really quick from the command line, as long as you're, of course, dealing with small data. Anytime you get over maybe 10 lines in your file, you're going to want to use something like less, which lets you kind of scroll up and down through the data. As things get really large, you're going to want to do things like head and tail, where basically show me the first 10 lines of the file, show me the last 10 lines. You can set up tail to like follow a log output file, so you can just see changes to the log as it's coming through. So here's an example of show me the first 4 lines of this players.txt file, right? So again, if you're going to be working in these type of environments, at least those are worth getting really comfortable with, and they're pretty easy, right? I mean, they do one thing, they do it pretty well. Probably the most complex is grep and find, but even those, just take a little getting used to. Some of the more powerful ones are I personally only use in very special cases. The 2 most common are this awk and sed. They're both very similar. They essentially process files one line at a time. Awk, generally speaking, is easier to use with files that have a natural delimiter in them, where sed can operate pretty much on any type of stream that's coming through, right? So awk, for instance, is really good. So you have a CSV file with 600 columns in it, right? And you know that you only need to get the 2nd through 5th and 37th through 52nd. You can write a short little awk command that'll grab those columns for you. Really, the only thing I've used sed for personally is if you have a large file and you want to do quick find replaces, you can write a little sed script that'll go through that file and do that for you. I was going to ask them what they use, but I guess they stepped out. And then there's things like sort values that I get from standard in and send them to standard out. And you need that, for instance, if you want to look at unique values. So unique depends on its inputs coming in sorted. Well, those are just Unix commands that are out there. So in this case, if I want to take that players.txt file and I want to see what are the unique values of the position, I could first run awk to get all the values in the 4th column, pipe that into sort so that they come through a sorted order, and then finally use unique to remove any duplicates that are there. Right? They have to be in sorted order so that unique can be as efficient as possible. In that case, it only has to keep one value of what's the last thing I saw. Is the next thing I see the same? If so, get rid of it. If not, output it. These I wouldn't necessarily worry about too much. Again, just knowing that they're there is probably enough. If you ever do feel like, oh, I need to figure out how to do this with awk, Google it. Google what you want to do. Somebody probably has asked that question, and you can find exactly the incantation of this command that you need. Mm-hmm. These slides will be available at some point. I got to get them to John, and he can make those available however he's doing that. Hmm? Yeah.
Have you ever used ag as a searcher in place of awk?
I have not, no. But that's a good point, though, because there are a lot of very similar tools that do very similar stuff. It's really just what are you most comfortable with, right? I would say that these are the most common that I've seen. Yeah. Most of the questions, how do I get the 4th column in a file? Somebody's going to give a solution that uses one of these, right? Yeah. Okay, but one big one, and it's kind of hairy. So a lot of these kind of depend on this, what's called regular expressions, right? Regular expressions are, more or less a standard way of expressing a pattern that you want to find. Many tools use these. Almost all tools, in fact, have some support for regular expressions, and that's because they're extremely powerful. The problem is that it gets really complex really quickly. it's impossible to remember exactly what the syntax should be for what you're trying to do. So again, it's a case where there's some tools out there to kind of help you. One of my favorite is the site regexer.com. Basically just gives you a simple form where you enter the type of text you know you're going to be searching through. It gives you a little input box for playing around with a regular expression and seeing what part of that text it's actually matching. So here's an example. So if you go to this tool, input these 4 lines. Say I want to match a regular expression that only finds this top line, right? That's all I'm interested in. So here's what my regular expression would look like. So I'm searching for the literal regxr. I have a escape character here for period. Period generally is the wild card in regular expressions. So I need to escape it in that case. If I hadn't escaped it, it would pick up both this one and this one, right? Because the wild card 2 is perfectly valid. So I need to escape it. Literal search on com. Another wild card plus means any number of those, any number of the previous characters. And then finally the regular search for foo. So you know that's a very simple one, and it's still kind of complex to look at and try to understand what's going on, right? But you can't really get away from these. They're extremely powerful, and you're going to need to use them at some point if you're doing any kind of ETL processing. You know, and at a minimum, get used to doing kind of wildcards. I mean, you can use wildcards in database queries. Pretty much any other kind of thing where you have to search. I mean, grep is basically, I guess grep has full support for regex. Usually all I need to do is do a little wildcard search for stuff, right? It's usually sufficient. So again, one level up is these scripting languages. You know, choose your favorite, right? These languages are higher level programming languages. They're not designed just for doing scripting, but they can be quite powerful for that. Most of them have similar support for doing standard in, standard out, so you can use Perl, kind of like Awkward said, if you want to, or you can actually write a full Perl script to encapsulate your business logic or cleaning logic. It's nice one thing that's nice about these is you could code up a bunch of stuff in Bash, and I guess it'd be the similar point, but as your logic becomes more complex, it's easier to modularize your code. There's usually full support for doing things like database lookups within the code. Every one of the languages has some way of talking to a database. And one of the best features about it is it makes it really easy to write unit tests. Are y'all familiar with unit testing? So unit test is very important concept in software development, even at this level. Basically, you can write tiny little tests that that you can run repeatedly to see if the logic you've implemented is doing what it's supposed to do. I guess it's a little bit out of scope to go too much more in depth with that, but it allows you to the power of it is you can write the test first before you actually implement the code, and then just keep iterating on the code until your test passes. And then if you ever change the code after that, you can still run your test again to see if that broke something, essentially, right? What's that?
You said you can test the code without code.
No, so you have a function, right? And you have one function that does one thing, takes some inputs, does some logic, does an output. You could have, your input. There could be like 4 different paths you could take within that function, depending on the input, right? So you can write 4 different test cases that make sure that function does the correct thing in those 4 instances, right? So you can write those tests first before you ever implement the function, and then as you're writing the function, you can keep running those tests to see if you've got the solution yet, right? Okay, so once you get the solution, you may not touch it for months, but you may come back in 5 months and realize, okay, there's a 5th type of input I need to handle, right? So I write my 5th unit test, implement the logic for that, and now I can run all those 5 tests to make sure that by changing the code to handle the 5th case, I didn't break the other 4 cases, right? So it helps you to helps you sleep better at night, essentially. And if you really do it right, you can make coding quicker and more efficient. So just a couple of probably biased opinions of Perl and Python. Perl is kind of known for being really fast, as fast as C, essentially. And again, you can use it almost like Awker said. It's very Every Unix system has Perl already on it. But the downside is it's notoriously hard to read. There's 100 different ways to do the same thing. People take pride in what's called like Perl golf, where they try to get the solution in as few characters as possible. So that, it just makes it, you do not want to take somebody's Perl code and try to figure out what the hell they're doing, right? Kind of on the other end of the spectrum is Python, right? So they're all about, I think a part of it came out of they hated Perl so much that they wanted to start a new language that had an emphasis on readability and just being easy to learn and understand somebody else's code. And the way they accomplish that, a big way they accomplish that is there's only one way of doing something for the most part, and the structure of your actual source code is very well structured. So it's all based on space delimiting, and there's only one way of doing the spacing of different pieces of the code. And it's all about making it really easy to read. It's great because there's a huge library of third-party packages. So if you realize you need to do something that's not in base Python, not possible in base Python, somebody else has probably already done that, and you can just go grab their module and start using it. The same can be said about Perl. Perl has a big ecosystem of that too. But Python can be a bit more cumbersome to get going. You do have to kind of manage your packages that you have installed on your system, and when you start needing multiple versions of Python, that can be kind of a pain. But there's tools out there to help with that. And I didn't talk about R here, but we're going to dive into R pretty heavily here later on. So, and then finally, we have kind of these GUI-based tools, right? So you build up your pipelines with these pre-compiled tasks, and also sources and destinations. You drag them onto your canvas, you link them together, and you build up your workflow that way. It's a little easier to get going. You don't really have to be a programmer to understand. You don't have to have any scripting skills, for the most part, to get those going. For me, it's a lot easier just to understand how data moves through the pipeline, because you can physically watch it kind of go through the different links. Whereas when somebody just gives you a script in Python, you still kind of have to understand which function calls which function, and kind of have to read the code to figure out how data is going to actually move through that script. Yeah, and a lot of the common tasks are already done for you. You usually get a little form to configure a database connection, for instance. You don't have to know how to call a particular function in Python in order to set that up. So again, two samples are the SSIS, which I used a lot early on, but now I've moved heavily towards Pentaho. So like here's an example of Pentaho, right? So you have these tasks, you have an input, you have all these different things you're going to do to the data as it moves through the pipeline, and then finally I'm going to write out to my output and maybe have some logging associated with that. So I'm actually going to pull up, I'm going to try, these resolution of this stuff isn't very good, but I'm going to try to pull this up. And so this is Pentaho's Java base, so it's really easy to download and get running. Let me see if I can get this lined up. Okay, so with like Pentaho, right? So you have two basic types of data flows. You have the job level stuff, where you basically have a start and an end, and in each step you can call sub transformations. So basically, this just wires up a bunch of sub transformations. So in this case, this is an actual ETL script that I developed working with the Weber Energy Group at UT. And basically, what we're doing is pulling market pricing data off of ERCOT's website on a daily basis. In this case, I set up the script so that I could either run it as a cron job, which we'll talk about a little bit later, where it pulls the current date from the system time and runs it just for that day, or I can give it a start and end date, and it'll loop basically based on those parameters and pull all the past data. One thing that's kind of kludgy about Pentaho, and it could be I'm just not doing it right, or they've improved this since I wrote the script, but kind of setting parameters and variables is a little kludgy. Like you need a whole sub transformation that does nothing but, get the system date, create some parameters, use a little JavaScript to actually get it into the format that I want, and then set that parameter here, which now is available to me up here, right? I'm not going to go too in depth on this because it's just too much to cover, but just trying to give you a basic overflow of how this works. But essentially, this is going to come into a loop, and here's the meat of this particular transformation called get new data. It's a sub-transformation. And so the other type of object in Pentaho is a transformation object. In this case, you need a source. You always need something to kick it off. In this case, I just have to generate a single row just to get the data flow going. Generally, you would have like a CSV file or a database table or query might be your source, but this is kind of a special case. You have this whole list over here in your design of the available types of transformations that are available to you. So there's, your basic inputs and outputs, CSV files, fixed file input, Esri straight files, which are GIS type data. I mean, there's probably twice as many as the last time I actually used this. I mean, there's really a lot of activity in this product. And eventually, at the end of your transformation, you're going to dump that out. So XML, database table, text file, Microsoft Excel output. And then all the rest of the stuff are types of transformations you may do. Some of the basic ones are here, like perform a calculation on a field, produce a new field, do some, probably the most powerful and that I use a lot are these scripting-based ones where you can have a little business logic in a script that operates on each of those fields. But in this case, I'm kicking off a flow of data. I'm actually going to go out to the ERCOT website and figure out the exact page I need based on this parameter I passed in. So this just happens to know how their web sites are laid out. I'm going to pull back all the HTML from that. And then I'm just going to pass that HTML down to this Java script task. And what's so nice about this is because it's based on Java, you can actually have access to basically any jar file out there, right? So if somebody's implemented some cool code, you can just use it directly from here. So here I'm going to use this JTidy package. And what it does, I won't go into the code too much here, but essentially it takes raw HTML output, which is semi-structured, but it may not have matching in tags, for instance, whatever. It's going to clean all that up so that it's technically valid XHTML, which means every start tag has a matching in tag, so on and so forth. And what that allows me to do is now that I have valid XHTML, I can actually start extracting data from that, right? So I can use a little XPath expression to get, a lot of data on websites is in HTML table documents. So you have, table, row, or TR is a row, and then several TD elements in there that is actual data, and then closing TR, new TR for a new row, more TD objects that you want to grab. So here I'm just going to go find those elements that I'm interested in that HTML, extract each of the rows, and now that becomes my output from this task, and I pass that along to the next task. So here I'm going to, I think I just do a little bit of cleaning where I truncate some of the fields. I can filter out some bad fields that I know to look for because I've looked at the data before and figured out what potential issues there may be. Do a bunch of cleaning of converting the way that they represent timestamps to make it valid with eventually the database where I'm putting this stuff. So for instance, they have like 24, which should be 00 to represent midnight in a database. I have to clean that up. Again, you can just do some simple in-place scripting. So just take the input field, replace 24 with 00, output a string with this new field name. I remember having a lot of issues with this, but I had to get in a very specific format that the database liked. So I can take that string and basically convert it to use this particular format, and then eventually dump it into a table, right? So I specify my connection, the table name, and then I can map the fields coming through my ETL pipeline into the database fields, and it'll just dump them in there. So it's kind of nice. So when you actually, I actually hadn't run this in a while here in development, but when you do run this, you know, these links will actually light up with like how much data is flowing through each one. So if like, you know, 1,000 rows make it to here and only 900 make it to here, you can then add in little loggers there to see, you know, the ones that didn't make it through. Let me look at those so I can see what, you know, what might be wrong with them. So, you know, pretty powerful stuff. You know, again, I recommend it especially for people who find themselves having to do this type of stuff and aren't super comfortable writing code directly. Although, as you saw, there's still a fair amount of scripting that actually ends up getting done here, but it's still a little less intimidating than writing a Python script from scratch. Close this out. Get back to, okay, so there's kind of three methods of writing up these ETL scripts. So what happens after you have it written up, right? How do you actually kick these off? Well, it could be the case that you only need to run this once or twice or on a very periodic basis every 3 months. So in that case, you can just run it by hand, right? Go execute your script, kind of watch the outputs and any error logs that you may have generated to figure out what's going on. More often than not, though, you're actually going to need to run this every day, every hour, every minute, essentially. So the way of doing that in a Linux environment is what's called cron jobs. And it's basically just a scheduled task that you can tell the computer to execute every so often, right? So here is an example. So this is the ERCOT job we looked at. So here's an example of I had my database server out there. I set up a cron job under my account that says, basically, at 3:30 every single morning, go out and run this particular bash file. And then all that bash file does is it calls my Pentaho executable, passes in some parameters, and passes it in that actual job file that I had, right? The key is when you're doing this, when you have to run stuff over and over, you generally still want to know kind of what's going on. So you can actually wire up your jobs to like send either a report email every day or maybe just send an email when something goes wrong. So it notifies you to go out there and look at it, right? That's really easy to do. But generally speaking, you can set these cron jobs up and kind of forget about them. I just wanted to expose you guys to that so you kind of had an idea of how you do something like that on Linux. Yeah, so conclusion for this. So there's no real way of getting around ETL. You're going to save your time by scripting stuff up and automating it. Don't do things manually for more than a day, essentially. Anything you have to do twice, it's worth scripting it. But you know, my advice to you guys would be to learn at least one scripting language. If you don't know any, I would start with Python because Python is so it can be used for so many different things, basically, and it's kind of designed to be easy to learn, right? Again, I'm a little biased towards R right now, but that's because I'm only doing data analysis and statistics with it, right? Technically, you could write a website in it, but it's not very good. Python's way better for that. And actually, I've only used Python for doing web development. It has some pretty strong data analytic features as well, which we're going to look at a little bit, but I use Python for web stuff, R for data analytics type stuff. But again, that's just me. The big key here is document what you're doing. As you're writing scripts, put a lot of comments in there. You're going to forget why you converted one value to another, exactly what your logic behind that was. It also allows other people that want to use the outputs of those transformations to have some confidence in what actually happened, you know. Usually, people are pretty lax about documenting their code. And at best, maybe you'll get a README file that gives you a very high-level idea of what's going on, and you have to figure the rest out for yourself. Get in the habit now of just commenting your code a lot. You can always hide the comments, you know, if they get in the way. That's one of the arguments people make is, oh, we have all these comments in the code, and I can't really read the code very well. Well, just use a GUI, use an IDE, hide the comments, you know, no issue. So I haven't talked about databases a lot. You'd asked a question earlier about SQL, right? If you don't know any SQL and you still have time, I would take a SQL class either through your school or there's some actual good content out there on Coursera and edX about it. It's a ubiquitous technology. It's not going away, and it's worth being comfortable with writing SQL queries and understanding the basic concepts of databases. Absolutely, and usually very high quality. Okay, I'm gonna take let's just roll right into R, and then we'll take a break after that, or roll into Python, and then we'll take a break after that before we do the R stuff. Close some of this out. Do you have any questions about ETL processing before we move on? No, I was pretty quick there, but Coursera is great. UT actually does all theirs through edX. I think we only have about 9 classes right now. I'm actually going to talk a little more about it, some of the courses I would recommend that I've at least audited part of. Let's fire this up. All right, so now we're going to talk about Python, and we're going to do it using what's called IPython Notebook. It's kind of the latest, greatest Python toy that people are using. Okay. Make that a little bigger. Okay. So the objectives of this are to basically give you an introduction to Python with a kind of a focus on how it can be used for doing data analytics. I'm going to talk about some of the interfaces you have to Python, some of the ones I recommend, as opposed to, some people really like and only do all of their software development using products like Vim, right? I can't stand that. There's so many nice things about IDEs and GUIs that I find make me more productive as a software developer and a data analyst that I highly recommend them and try to push it on all people. Again, it's usually old timers that feel that way, but a lot of people at TACC that are around my age are Vim people, Emacs people, but that might be an anomaly, I'm not really sure. Yeah, we'll just kind of look at basic Python syntax. Again, I can't really teach you guys Python that haven't ever been exposed to it before in 40, 45 minutes, but we can look at some of the basic syntax, give you a feel for it. And I'm going to specifically talk about 3 kind of third-party packages for Python. One is Pandas, which gives you the ability, it's a data structure essentially that gives you high-performant ability to work with data in kind of a Excel spreadsheet type way. Well, I probably shouldn't say that because you don't actually touch individual cells, but in a tabular way. It's like tabular data in a very high-performant way of working with tabular data. Matplotlib, which is a very popular plotting library for Python. And then finally scikit-learn, which basically implements a lot of these machine learning algorithms so that you can do machine learning pretty easily on your data sets. So just a little bit of history. Again, Python is very much a multi-purpose, full-body programming language, and it came again out of having a strong emphasis on simplicity and readability, sometimes at the expense of performance even. It is an interpreted language, right? So it's not first compiled down like you would do with C. So there are some performance hits that come along with that. But the trade-off is it's a lot easier to develop with, right? You don't have to compile first before you execute your code and see what it's going to do, right? You can just do it on the fly, right? I find that very powerful. R is the same way in that regard. It has this, a lot of its readability comes from being very strict about spacing, and particularly in using like tabs, and we'll kind of see examples of that. But in my experience when I was learning Python, that was kind of a pain in the ass, because if you had this whole Python script and your spacing was off by 1, it would error out, and you'd have to go find exactly where that was wrong and blah, blah, blah. Again, another reason GUIs help is that if you have a GUI that knows Python, it can auto-format it for you, and it usually does a pretty good job of that. So, generally, there's one and only one way of doing something. Yeah, so one of the things that I personally don't like about it, about this philosophy, is it only has single-line comments, right? You can't do block comments and easily collapse those down like you can in some of the other programming languages. So, just one thing I find annoying, that is just a result of this type of philosophy of let's only allow things to be done in one way. It is a very mature open source project, completely free. It's been around a long time. It was an offshoot of ABC and developed by this Guido van Rossum, who is now known as the benevolent dictator for life of Python. Linux guys have weird egos. So it has a reputation for being easy to learn. You don't have to do all the compiling, linking of third-party libraries, etc. You do still have to install third-party packages, which can be a pain. And I'm not going to dig into too much of how to do that here, but there's tools like pip that allow you to more easily kind of manage that on your system. Lots of third-party packages and complete frameworks out there. So that's one way that this differs a little bit in R, is that, you know, take something like Python Django. It's a complete framework for doing model view controller type web applications, and I actually have worked on a couple of those here. Again, I use Python mostly for web type work, and it's very good for that. Again, it's an interpreted language, can be slower than C or Fortran, but there's ways around that. Is that you can a lot of the high performance stuff that needs to happen, like pandas, is actually implemented in C or Fortran, and Python just kind of gives you a wrapper around that to make it easier to work with that underlying code. Why we care about Python here at TACC, where traditionally our main community has been C, C++, Fortran, is that there's been an explosion in popularity in the 2000s. It's actually pretty well established in the scientific computing community. A lot of the performance investments have come out of academia / scientific computing. There's actually a very, very strong Austin Python base. So we have a lot of user group meetings and meetups. And there's a lot of good resources just here in the city of Austin. A lot of startups that are based on Python. And it's all about really, you know, scripting allows you to reduce time to solution, because it's not always about how fast your code works. It's also how long it took you to develop that code and how much time you have to spend maintaining that code, right? So you have to reduce all phases of the software development cycle, right? It is increasingly popular for data analytics. A lot of that has to do with these packages that have been developed for it. So data cleansing, manipulation, working with tabular data, you have this pandas package. It does have some support for statistical modeling and doing hypothesis testing and things like that with the stats models package. I personally have found it to be pretty lacking, especially compared with R, although that's not really a fair comparison because R was developed from the ground up as a statistical tool, right? This machine learning scikit-learn, sklearn, is quite powerful, and it's relatively young. I don't even think it's to version 1.0 yet, but it's there's a lot of activity around it, and a lot of your most common algorithms already implemented in it. And finally, matplotlib is a third-party plotting library to make much fancier plots than what you get out of the box with Python. And then I wanted to show, it's almost a little too big. So here's a survey from the Strata conference, I think back towards the end of 2013. Strata is a big data / industry-focused data analytics conference that, again, is your Revolution Analytics, your Twitters, Facebooks, Googles, SQL Server, you know, these type of companies, more industry-based type conference, but they ask the attendants, what are the tools that you're using on a daily basis? And far and away, everybody's going to be using SQL in some form or another. Like I said, it's a pretty ubiquitous technology. But it's interesting to see that the next two are R and Python. So these would have been probably down here about 5 years ago, right? SAS would have probably been up at the top. But as these become more mature, and especially because of the community that's around them and that has been publishing these third-party packages and extending the functionality of the tools, they've really grown in popularity. Actually, this used to be at the top. Excel used to dominate. But Excel is, as things get more complex, just becomes a complete pain to use, even though, I mean, it is a pretty good product. So speaking of GUIs, and I have to adjust this a bit. So some of the GUIs available for doing Python are, the one that I use is Eclipse. Are y'all familiar with Eclipse? Probably the software developers are. A lot of people hate Eclipse. They call it a big, dull instrument, as opposed to like a small, sharp scalpel. So it does a lot of things, but it kind of plods along. It's like we try to do everything, so we're this huge beast of a tool. I personally have a love-hate relationship with it, but I've invested enough time over the years in learning it that I can be quite efficient with it now. It just has a very steep learning curve, right? There's so many things it tries to do, so many places to configure options that it just takes a long time to learn. Because it's not specific to Python, right? It's really came out of the Java community. You can do Java programming, C++, pretty much whatever. There's going to be an Eclipse plugin for it. The most popular one for Python is called PyDev. But I like it because it integrates a lot of things like egit for doing and Subversion for doing source controlling. Have they talked about source controlling at all? Source control systems? So if you're doing any kind of serious software development, even scripting, even if you're just writing a one-off script to do ETL processing, you want to use source control. So what source control does is you have your code checked into a system. You make a change to that code, you check it back in, it tracks the changes that are made. Okay, so maybe you go through 50 changes to your code and you realize you did something wrong. It allows you to go back and look at what the code looked like 10 changes ago, 12 changes ago. It becomes invaluable, especially, it's good for even if it's just you working on the code. If it's you and any number of other people where they could be changing the code at the same time, it handles all the integration of doing that. It's really an invaluable tool and one that's definitely there's a learning curve to it, but it's definitely worth that learning curve. Git right now is the one that's all the rage. It's more difficult than Subversion. I would suggest, if you're going to look at it, start with SVN because it has a simple checkout, modified check-in mechanism, where Git has this whole bigger ecosystem that is popular because it provides more power, more flexibility, but it's definitely much more difficult to learn. So here's an example of this is a website basically that I work on, and what I really like about using the IDE is it does a lot of things like step-through debugging, so I can put a breakpoint in my code, interact with the website. When this code gets hit, it'll break down into here, and I can see all the information I need to see about it, right? Kind of at the other end are kind of very specific GUIs for that particular language. So here's one called Spider from Inthought. Inthought's one of those scientific computing companies that is from Austin and has been a big champion of Python and doing data analytics in Python. So this is a GUI very specific to doing Python. I've used it a little bit. But again, I don't do a lot of data analytics in Python. If I was, I would probably be using Spider. Oh God, no. No, that's notoriously not underdeveloped, really. But I will say, so for Python, what's getting all the attention now is IPython. And IPython is basically what we're doing right now, right? You have this little notebook that you create, and what it allows you to do, I haven't really shown it, but it allows you to quickly add new content. So I can have just some basically HTML in here. It's like a what you see is what you get editor. But then you can break down and actually type in code directly in this notebook, right? Oops. So I can mingle documentation, presentation directly with my code. So this is the GUI that everybody's using right now. It's this IPython stuff. It's kind of nice though because once you finish this, I can just send this notebook to somebody else. They can open it up and then start interacting with all my code. There, you can deploy the notebooks to a server so that people can go to a URL, pull them up, and interact. It's all, you know, browser-based type stuff, right? So, basic syntax. Python is an interpreted language. You don't have to, as in C, where you had to say this is going to be an int, this is going to be a string. You don't have to do that here. I'm not going to do as much interactive typing just because it's kind of hard the way this is set up, but you could you know, just play around with the syntax directly in here. So if I assign A to 2, B to 4, 2 to the 4th is 16, I could do A divided by B, and then execute that again. Oops. Oh, let's do an integer division. Essentially what the output will be is the last line in here. But it allows you to, you know, quickly type some stuff in, and it controls the input-output. It's kind of similar to what you'd see if you're working from the command line, but it's nice because you can just quickly go insert new, insert a cell. That can either be a code cell, it can be a Python markdown cell, it can be a raw text cell, so on and so forth. See that there. So again, so, you know, the other type of data types has your typical ones. Here's a string. I can set C to a string and then print it out. What's nice? One thing that's nice about Python is the way you interact with strings. So here, you know, C is my string variable. If I want to do a substring, I don't have to call some other method, right? I can just do indexing of the characters I want. Oops. So that's very convenient. One of the key strengths of Python is its text manipulation capabilities. Here we define a function. So here's an example of how the kind of white spacing structure works. So you know, when I hit return after a semicolon, it knows to space it by exactly 4. If I wasn't in IPython and I had one extra space there, then this whole thing just basically wouldn't work. It would give me some kind of cryptic error. I'd have to try to figure that out. But you know, that seems pretty clean, right? So define function add, give it a b. I can give b a default parameter so that I don't actually have to supply it. So if it's not supplied, let it be equal to 1, and return a plus b, right? So here I can do either I can pass parameters by specifying the parameter name and its value. I can do it by position. And then for default parameters, you don't have to supply it at all. If you don't supply it, it's just going to use whatever the default you set is. So the other thing is, because you're not declaring exactly what A is, you can change it on the fly. So here I set it to an integer, print it out, change it to a string, print it out. I don't get an error with that. If I did try to use that variable now as something that it's not, I'll just get that type of error on execution time as opposed to compile time, right? And for the most part, Python errors are pretty helpful and explanatory, especially if you're in IPython. It shows you exactly where the error occurred, and that, if you haven't done a lot of programming, that's really quite invaluable. Huge time saver. Okay, so that path is still right. Here's how you would import third-party packages. In this case, the operating system package is built in, but I have to import it before I use it. So I'm going to import the operating system. I'm going to call os.get current working directory. So that returns this particular folder. I could actually change into a different folder and run these commands to see what's in that folder. And the whole point of doing that is it just makes, when you start importing data or referencing things, you can reference it from a relative path instead of having these super long strings everywhere, right? I think that, yeah, I should. So another nice feature of using a GUI is you get auto-completion. So if I do dot tab, I can basically see what all methods are available for me. In this case, of course, there's a lot. It's a pretty fundamental package in Python. But it's a very nice feature. I think you also get, yeah, complete code completion. So if there's only one function that has those first 3 characters, it'll just complete it for me. Oops. Basic data structures in Python is you have your lists. Lists are mutable and they can have different data types in them. So here I have a list of an integer 1, 2, and then the character C. That's how my list looks like. I can easily add new objects to my list. And, remove objects. And this really gets more technical into computer science. So basically the different data structures give you different type of performance depending on what you're doing. So for instance, a list has, I think, constant access to the last element and the first element. So you have methods like pop that are going to run in constant time, whereas different data structures have different runtime complexities depending on what you're doing. Very much above and beyond what we're talking about here today, but just something to keep in mind. That's why there's so many different data structures, right? That's why everything's not just a list. There's a reason for it. So here we have dictionaries, which are basically key value pairs. They can have different value types. All keys, I believe, have to be strings. You have tuples, which are basically immutable lists. You have sets, which can't have duplicates. Again, it all comes back to runtime complexity of the different data structures. Okay, so as far as data analysis goes, the type of data analysis that we've been talking about, statistical analysis, machine learning analysis, much of it in Python makes use of this NumPy package. NumPy, again, is a product of this company, InThought. It's open source. They made it open source, but it originated with them. And essentially, it takes all of the hardcore data processing task and has C code written to execute it. So you call it from Python, NumPy, under the hood, run C code to make it really fast. Pandas is even a layer up from NumPy. It's built on NumPy, but it allows you to basically work with data as like a data table, which isn't available out of the box in Python. So here I can specify what's called a data frame. It's the same concept that we'll see when we're working with R. I give it an index column, which is going to have 10 values ranging up to 10. I give it a category, which is a 10-value list of A's and B's. The first 5 are A's, the second 5 B's. And then value is just going to be some random number between 0 and 100, I think. Between 0 and 100 by 5, grab 10 of them, right? So I can do df.head to see the first, I think default mine is 5 values. One thing I should note is that it is, Python is 0 indexed, which means that some languages are the first index in an array is at 1. C, Fortran, all those are going to be at 0. R is different in that it is indexed at 1, just something to keep in mind. So now I have my data frame. I can say a lot of the performance comes from basically having indexes on your data structure. Oops, did I do this right? So very similar to like a database concept where you have a column of values in your table, you create an index on it, it gives you very highly efficient access to that column's data. So by default, it's going to use the first column as the index. I can call this describe function, which just gives me kind of a basic summary of my data, how many values, what's the mean, standard deviation, so on and so forth. Where this gets really powerful is the ability to, as this table becomes very, very large, lots of columns, lots of rows, I can very easily slice and dice the data. So here I can say, give me the first 4 rows and only the, or I guess I changed that. Give me rows 0 to 3, which would actually be 3 rows, I believe. And just the 0 through second columns, right? So basically row names, or IDX, category, index, right? So it allows you to very quickly just slice and dice your data. It allows you to very quickly sort your data. And again, it's because it's implemented in C under the hood, it's very fast. That's the whole key. That's why you want to use these type of data structures. I can do selection, so give me all rows where the value is less than 50. I can do aggregation, so group all my rows by category and perform the sum. Get the results of that. And of course, I could be saving all of this, right? Each one of these calls into a new variable if I wanted to. So new. It does deal, I won't go too much in depth with it. It does have, though, first class support again for kind of missing values, which is a very technical aspect of this. But basically, a lot of times if you had missing values and you try to do an aggregation and one of the values is missing, it would just error out. If you have first class support for it, it knows how to handle those missing values. And we usually tell you it saw it, but we'll still go ahead and do your calculation for you without giving you an error. I can merge 2 different data sets together based on a join column. And then again, all this stuff is very SQL-like. So if you're used to using SQL, this kind of gives you a way to interact with your data that you're used to, and it's very fast. So that's Pandas. That's a very quick, high-level overview of Pandas. Looking at matplotlib. So matplotlib basically provides you with what's kind of known as a grammar, a graphics way of building plots in Python. Basically what that means is you have multiple statements essentially that kind of build your plot up one kind of aspect at a time, right? And in the long term, it makes it a little easier to manage all the little bells and whistles that you might want in your plots, especially for publishing papers. You know, you want very shiny, nice-looking plots. And if you did that everyone in Excel, it would take you forever. If you changed anything, you'd almost have to start over. That's why instead you would like to script all that up, right? So you can just execute the script, you know, change your analysis, re-execute the script, get all your plots and stuff for your paper. So this is doing basically, we call NumPy to get my random number generator, import matplotlib. If I import it in this way from matplotlib, import pyplot, it allows me to just call, it's a little shorthand for how you access it. Actually, this as command. So I import NumPy, but I want to give it an alias np because it's just easier to write. Here I'm only importing pyplot, so matplotlib might have a ton of these different packages. If I did import matplotlib, I would get everything. I really just want pyplot. I'm going to create a data set, which is 100 random normal variables. I'm going to create a histogram that has 10 bins. I'll give it a title, and then finally I'll actually call show to plot it. Okay, so here's our histogram. Because this is random, if I ran it again, I would get a slightly different plot, right? We're doing random execution here. Here's a little more complex, shows how to actually do multiple plots, multiple graphs per plot. So I'm going to have 4 sets of variables of normal randoms ranging from 100 up to 1,000,000. And I'm going to create a figure that has 4 essentially areas to plot, 2x2 subplots. On each of those, I'm going to do a histogram and give it the same number of bins. And this basically just shows you, the central limit theorem at work, right? So as the number of random variables I have increases, the more normal-like my data is becoming. So these are just an example of just some kind of nice, how easy it is to create a pretty robust chart. So I'm trying to remember exactly what I do here. I give it a range between I forget exactly what I was doing here, but I think most of these are examples from the Matplotlib's gallery, which we can zoom through real quick just to see the power of what this actually has. But here's your typical pie charts. And again, it's just a couple lines of code that allows you to do that. Obviously, you wouldn't need to. You're not going to memorize exactly how to do these. That's why things like the but you can go, of course, to their documentation. And if you have an idea what type of plot you want, then you can go click on it and get an example, essentially, of how to do that. And then you can tailor it to your own needs, right? So it's pretty powerful. As the plots do get more complex, yes, it does take more code, but again, a lot of this is just aesthetics. So giving it a title, changing the coloring, blah, blah, blah. So this here is a kind of a heat map plot of, I forget what type of data, but again, that's by far the most popular plotting library in Python. It is more focused on kind of generated plots as opposed to interactive plots where you do something like JavaScript or something else, but it is pretty powerful and pretty easy to use. Finally, so we have scikit. I think this is the last thing we're going to cover. So scikit-learn. So this essentially provides access to a bunch of machine learning algorithms directly from within Python. So how does that work? So think about it. So everything from generalized linear models, which is like linear regression, logistic regression, support vector machine, gradient descent, clustering, naive Bayes, decision trees. Those are all very specific to doing different type of either categorization or prediction. So one that we'll look at in just a little more detail is what's called naive Bayes. It's fairly easy to understand just because it's relatively simple. I mean, it's naive, right? It's essentially what you're wanting to do is you have a bunch of explanatory variables, right? You have n explanatory variables. You want to predict the category of y. So you're saying, what is the probability of being category y given that I have these characteristics x1 through xn? Well, Bayes' theorem says that, well, that probability is equal to the probability of being a y, being that category. That is the probability of having those characteristics being that category divided by the probability of having those characteristics. The reason this is important is because you can build these. You have this information, right? If you have training data, you can calculate the probability of being y. You can calculate the probability of having those. Actually, there's a fundamental step I'm not showing here, but you assume independence between all these, so that this actually turns into probability of having feature x1 given y times probability of having feature x2 given y, so on and so forth. So it's called naive because it assumes that those two things are independent, where in most cases they're not. So like, if you're analyzing a book and you want to know if it's about baseball and you see the word bat in the book, there's a higher probability you're going to also see the word ball in that book. But even though it's naive and has that assumption, it still works pretty well in practice. And so here's how you could actually implement that in Python. So here we're looking at that iris data set that I kind of talked about a little bit earlier. And essentially, it's going to, a lot of these packages will come with these kind of toy, I shouldn't call them toy data sets. They're usually real data sets, but they're kind of ones that the community usually knows about and kind of uses in a lot of their example type stuff. So this one is petal and sepal lengths and widths of plants, of these particular type of plants. So I'm going to first load that data set from this data sets library in scikit-learn. I'm going to import the naive Bayes implementation of Gaussian naive Bayes, which is based on the normal distribution. Iris is going to have essentially 150 rows of plant data. So what I'm going to do is set aside 120 of those as my training set. So I'll just take the first 0 to 120 of the actual data, the data being the x's, the characteristics. And then the labels are the y's, essentially. So I'm going to set aside those as well. Then I'm going to set aside some test values so that we can see how good our algorithm actually performed. So I'll grab the last 30 basically rows for that. I'm basically going to build up my model, so call Gaussian naive Bayes, fit these x's to my labels, and give me back a model. And now I can use that model to actually predict labels based on the test values, right? These 30 data points I set aside. And the way we'll look at how well it did is we'll just say, okay, I know what they should have been, because this is a supervised learning algorithm, and I can look for cases where the predicted value did not match what it really should have been. And it turns out, in this case, out of the 30 examples, I only mislabeled 2. So that's pretty high performance for a very, very simple algorithm. And again, that's all it takes to run these very powerful machine learning type algorithms, at least in a simple case. It turns out when you're doing this for real and you're not having a pre-cleaned data set, this may not change much. What's going to happen is you're going to have another 300 lines of code that takes your data, cleans it up, gets it to the point that it needs to be before you can call this method, right? Here's a very easy, a very quick example of doing linear regression. So I'm going to predict the value y based on my beta 1 times my prediction, my explanatory variable plus some intercept. So I'm going to fit an intercept and a slope essentially. Here I call scikit-learn linear model. I'm going to plot my results with matplotlib pyplot. And this is just a contrived example. So here's my regression model. I'm going to pass it in these x's and these y values. Fit x to y. Look at, let's see. Right, so I'm going to do my fit. I'm going to get the parameters back out. So these are the parameters used in doing the fit. Do I fit an intercept or not? Do I normalize the data or not? Blah, blah, blah. I want to pull out the coefficient. So this is what it calculated for the slope value, the beta 1. And here's the r squared, which is basically a measurement of how well it did. And it's just a simple plot. So here's the actual data points. It fit this simple linear model to it. So these are basically going to be your errors, the gaps between the fitted line and the data points, and it fits it in such a way as to minimize the sum of all those, right? So pretty simple stuff. The rest of this goes into how you would actually go about running Python. I originally did this for Maverick. It's very similar for Stampede, but basically y'all learned about modules, right? That's how we kind of manage our software and our systems. This is just how you would load Python. You can run it interactively if you start up one of these like srun viz nodes. I don't know if you've done that yet, but it's kind of a nice way to, again, one of the strengths of Python is being able to iterate on code right there at the command line or at the prompt so that you can see what's not working and try to fix it. So you can even do that on our systems using something like the viz queues or the development queues and get immediate feedback about what's going on with your job. This is just how to actually set up Python to run as a batch job, which is a little above what we're doing here. We're actually currently working on getting this interface to run directly on our backend nodes so that you can launch a job, go to your web browser, type in stampede.tac, some port number, and pull up this interface to interact with your data. There's some security issues we haven't quite worked out there yet, but we are getting to it. That's it for Python. Do you guys have any questions? I know that was really quick, but again, there's only so much we can try to do it one day. I know you guys are probably tired, so. If no questions, let's start back at 2:30. Just go ahead and knock the rest of it out. And yeah, see you guys in a few. Yeah.
No, she's swapped. Like she's working with this psychology. She's studying sexual relationships. She's like swapping men and women's not in a relationship. She's just it's just funny relationships. Arnold.
He's ostentatious.
Yeah, they're ostentatious. That's Woody. I don't know what. I was just wondering, I was like, is your name Austin or Arnold? I knew it was Austin. What was
His name is Arnold.
XC? Yeah.
XSED.
Did y'all know Facebook had other messages?
Yeah.
So this whole time I thought nobody was interested. So these people are
Hearing other messages. What are they? I said, are you?
I'll have it. I'll have it. Did you meet the people? Just meet the people. What?
What does that mean? No, I know. I have to reply back on my phone so that next week. So I can type it in from my phone. Yeah, I know. But keep bringing it every time.
That's just it's on my phone.
What's on the website? This
Yeah. I just type my profile.
Y'all are supposed to go on a break.
Yes.
Okay, we're doing a video shoot, but if you want, you can speak out now. And then we're just gonna ask you to give us a little space in the third. You can speak out now before we get started, if you need to do like this. Otherwise, we're gonna need your public speaking. We're doing a video shoot.
For how long?
Probably about 20 minutes.
That's fine.
So you need to speak out for the rest of the time. Sorry about that.
John, you keep going in and out of this.
Yeah, because this thing kept going. This thing kept going.
Just mute it on, you can mute it online.
How do we'll be on this?
You'll be on your cell phone.
How do I do that?
Oh wait, I don't know if you can do it on like, do you have the app?
No, I only have one.
If you have, hold on, if you have the app.
I don't see the app.
But go to your settings.
Where's the settings? Right there?
Yeah, I don't know if you can do it on the website.
Shut up, I don't want some guy. This guy's over here trying
If you download the app, look for this. Oh, click stop messages.
Okay.
Or if you have the app.
Yeah, I think I have like 90 days to turn it off.
And then you can turn it back.
I have like 90 days messages.
Oh yeah.
Definitely.
No, most of the time we're at home now, Damn. I thought you were going to turn into 7 real fast.
Where'd she go anyway? Say where she went?
Where did she?
She wants to be about.
Oh my god, what is the water one? What were you looking at? Looking at?
He searched watermelon, baby. Search watermelon.
Why? You know, when some people's pregnant, seems like they, it looks like there's a lot of water done. Check out, so that was water. That's what came up.
Emily, have you seen the video of a baby in a watermelon bottle?
And you said that earlier. Oh, I thought you were talking to
Maybe.
Oh.
Missed something?
I want to see that video.
Yeah.
I don't know, but I'm about to watch your baby's for the first time. No. Not that, but. You're so mean. That's baby water. It's so cute.
We'd like to have so many introductions with stuff.
This is so cool. Arnold, this is the cutest video. I know, right? I just keep watching baby feet love it.
Was there a summer class? I took a, are you at UT CS? Yeah. I was in the business school at UT. I ended up taking like 3 or 4 CS classes, but they were all high level intro programming and stuff, right? Never made it to assembly code operating systems. And I'm happy I didn't. And those are pretty brutal. Yeah. Have you ever tried to read like the Art of Computer Programming? You know what I'm talking about? Donald Knuth. Yeah, that guy has this whole made-up language that he teaches it all in, and it's like close to assembly code. It's like, no thanks. Oh shit. All right, let's just go ahead and get cracking on this. So our last section is on the R programming framework. I do have some slides here. I don't particularly like them that much. They're kind of a mismatch of ones I borrowed and kind of added to, but we'll just kind of breeze through these. to get a little bit of background on R, and then we're just going to play around with R a little bit. If you want to, while we're doing this, I know you guys all have different systems, but if you're interested in actually maybe learning R or following up on R after this, go ahead and go to like rproject.org or RStudio and download the RStudio and the version of R for your platform and install it. So then you can kind of follow along as we start playing with stuff here in a bit. It's usually on Macs and Windows really easy to install, really on Linux too. I'm sorry? Yeah. Just Google it. I mean, it's like r-project.org. It does, but you're not supposed to run it on the login node, and getting a job on the backend node. Yeah. Yeah, IPython's a little, like I said, that's why it's a little more difficult to get up and running with Python. You should be able to go, yeah, you need pip install. It's a lot easier on Linux than. Talk to me after this and we'll try it. We can look at it. I'm sorry? Oh, it doesn't matter. No. There's one in Dallas, like Revolution Analytics, but it doesn't matter. But yeah, if you go, I think you have to install them separately, if I recall. But yeah, you can go to our project homepage, download, and here's your different versions.
We have RGUI on this laptop.
RGUI? Yeah. I hate RGUI. You can install R. I recommend installing RStudio. It'll find your version of R and should configure itself. And I'll try to convey why I like RStudio better than RGUI. Basically, it comes from watching a lot of old professors teach R in RGUI and fumbling around with the different windows it pops up and just getting annoyed. But okay, let's jump into these slides. Like I said, we'll just kind of breeze through them. So R does have a pretty extensive history. It was developed by these two guys out of the University of Auckland, New Zealand. It had a predecessor called S. S you're never really going to see around anymore unless you're in a very, very specific field of study. I don't even know what that field is anymore, but it still basically is syntactically equivalent with S or compatible with S. And I guess the point here is that it has a very strong statistical background. It was written by statisticians for statisticians, and so it still has, it's the best, definitely free statistical program out there. It suffers a little bit from being so specific to statistics as far as features, performance. It wasn't written by computer science guys, that thought about performance first. But that being said, it's grown a lot. The other communities have adopted it, especially over the last 10 years, and have really kind of pushed it forward to being a really general purpose analytics-based tool, not just a statistical tool. And one of the most important things is in active development. You probably saw more development over the last 2 years than it has in the first 20, right? I mean, it's really exploded in recent times. So it's in a programming environment. It does have its own language, syntax, way of doing things. Its core packages are access to a lot of statistical functions, so access to things like generating random normal variables, random Poisson variables, chi-square variables, stuff like that. A lot of the statistical tests are there out of the box for doing statistical inference and hypothesis testing. Probably the thing it's probably most famous for, I guess, is its plotting and graphics capabilities. That's why a lot of people end up jumping over to R initially, is to gain access to those powerful tools. It does all of the kind of ETL type stuff here that you have to do anytime you're working with data. Whether it does it better or worse than others is just a matter of opinion. And increasingly it has a wider selection of data analysis functions, particularly implementations of a lot of the machine learning algorithms that we're interested in and other types of analysis. It has all your basic programming type structures, loops, branching, subroutines, a little bit of object orientation. It's not as fully developed as something like Python when it comes to like object-oriented programming, or and it also has, which we'll look at a little bit, one of the rules in R is that you don't want to do loops. There's ways of vectorizing your code so that you don't really need loops in most cases. And so that takes a little getting used to, especially like if you're coming from a Python background or some other programming language and you're used to writing for loops. Usually in R, you're going to see things done as using what's called these apply, sapply, lapply type functions. And we'll take a little look at those, but they basically do what a for loop does, just in a slightly different, syntactically different way. Again, we saw the slide earlier. I just emphasize again that R has been steadily climbing this list over the last 5 to 10 years. Its most direct competitor, I would say, is actually SAS. So SAS is a very expensive statistical programming environment. I wouldn't even call it programming. It's more like an advanced calculator. I have to use it in school. I absolutely abhor it. Just because I'm coming from the programming side, it's just really hard for me to use. For people that don't have any programming experience, they seem to like it because it's, I don't know, easier to just learn the commands you need in SAS than it is to think about doing things step by step in a typical scripting / programming type of way. I don't see how they're going to continue to compete with R now that it's gotten so good and has so many of the features that SAS has. I mean, SAS just hasn't innovated in a long time, but somehow they're still making lots and lots of money. Actually, the reason is because SAS is proprietary. A lot of like FDA trials require companies to have like fully supported software that's been highly. One thing SAS has is a whole army of PhD students making sure that every function in there is just statistically correct, essentially. And so when you're doing drug trials, things like that, sometimes the funding agencies require that you use SAS. So that's going to be something that's hard for R to break. That competitive advantage. But again, here's where you can go and grab R. Again, it's available through the module system on our systems. And generally, when you fire up R on Stampede, for instance, you're just going to get the command line interface to it. So you're going to get a new prompt, and you can start typing in commands directly into that prompt. I don't like working that way. It's just kludgy to me. I really love this tool, which is RStudio. So this is a GUI / IDE. It's unlike Eclipse. It's very specific just to doing R stuff. And I'm not going to go into too much depth in these slides because I'm actually going to run some code in RStudio and I'll point these things out. But just real quick, it kind of breaks your interface down into 4 panes. You can reconfigure this however you want to, but essentially you have your source code up here, your interactive console down here. Anytime you plot or call a help command, it will show up in this pane. And then up here, you're going to get a full history of everything you've typed in, plus the ability to click on a tab and see all the variables that you currently have in your workspace. I really need a better image of all this, better resolution. It makes it extremely easy to install the over, I think, 6,000 third-party packages available now. And there's some nice viewers to, generally speaking, you're going to be working with tabular data, like we did with pandas, and it's really easy to pull up a little snapshot of that to kind of see what you're working with. Higher level features, you got your interactive help, which will pull up your help pages over on your your display pane. It has this notion of having a project-based interface, so grouping files and data files and source code into these project folders and being able to save your environment. So any variable you have loaded, you can save at the end so that when you open that project next time, it reloads all those variables into your working environment. So those type of concepts. And it also has, again, that source control integration that I highly recommend you guys use if you get to write any kind of serious source code or scripts. We do have support, kind of like we're trying to do with IPython. We do have the ability to launch RStudio on Stampede and Maverick. I think it's broken on Stampede at the moment, but it works on Maverick. Basically, you launch a job. Once your job makes it through the queue and onto a back-end node, it starts a RStudio server, and then you get notified, and you can go to this link, and you can basically log in with your TACC credentials directly through your browser, and then interact with RStudio through your browser. And then what's important is your environment here is all the stuff that's out there on the Stampede file system, essentially, where all your data files and scripts and stuff are. I didn't actually create this slide, but it actually is a good point. I mean, R really can just be used as an advanced calculator. And I actually find myself opening RStudio every time I need to do any calculations now. The reason is, as things get any more complex than like that first line, it's just a lot easier to type it in. And if you make a mistake, it's easier to go in and retype it. You know, if you're doing it on a TI 85, 87, or whatever, it's just kind of a big pain in the butt. But it has all of the basic calculator type steps that you can do. And but of course, that's not where the real power comes from. The power comes from doing scripts. Scripts almost always involve some type of variable. R keeps it pretty simple. You basically have numeric variables. So there's not a big distinction between ints and longs and doubles and all this kind of stuff. It's just numeric. You have character variables. You have logical variables. True, false, etc. Again, it's interpreted. It's a dynamically typed system, so I don't have to say what A is before I assign it. It can just be A equals 49. Same with character string, or same with strings, and then C equals 1 plus 1 equals 3. That's false, so it saves the logical variable C as false. One thing to notice is that everything in R, all your variables are actually lists, essentially. So I said A equal to 49. That actually gave me a list where A, the first element of that, is the variable or the value 49. You have to get in a habit of always kind of thinking in terms of arrays or lists in R. That's one of the things it's harder to get your head wrapped around at first. There's two ways of assigning values in values to variables. There's the old school way of the I don't know what you call that. Arrow dash, essentially, or you can use your more traditional, with other programming languages, equal signs. I will say that even though the first way is older, it's still the predominant way that you're going to see code. So they're completely equivalent. It's just generally speaking, you're going to see the first more often. As these functions for doing for quickly creating list of characters. So here I can. The C means concatenate, essentially. So it very quickly gives you an array of 5 numeric variables. I can input those directly into the console using the scan function. I've actually never used that, but it's apparently there. And this one I do use quite a bit. So if I want all the numbers between 1 and 6, I can just quickly enter it that way. Here I can do a sequence. So give me a sequence from 1 to 6 by 5. That's pretty handy when you're kind of doing plotting and stuff like that. You want to control what's on your x-axis. And so, pretty basic stuff. Again, I kind of mentioned this earlier. This R does in its core package. You don't need something like NumPy to get this functionality. It has first-class status for missing values. And there's a lot of kind of sub-routines in R that allow you to deal with that type of stuff. So how do you want to treat missing values whenever you're looking at the max? Things like that. So for here, right, you run max without it, it's going to pick up that missing value and return it. I can say to remove missing values true, and I'll get the maps that I actually care about. Again, your basic data structure is always a vector. It is ordered. Even a single number is always a vector of 1, and is 1-based indexed, not 0-based. A matrix is a rectangular table of data. The thing about a matrix is all the data elements have to be of the same type. And a vector, again, also does have to be all of the same type. If you have different types in your vector, then it's a list. And you can have named lists, so you can give it basically a key value. My keys can have, or my values can be type characters or Boolean or numeric. Here's how you would access a named list element. So my list element returns value, or I could do it based on the position in that list. Hash table, it's there. I've never actually needed to use it, but it's kind of one of your classic data structures, and apparently R does have first-class support for it. The thing about hash tables is that basically you get constant lookup of values based on the key. So it's very fast for doing lookups based on the key, no matter where it is in your list. The main data structure that you're going to work with in R is called data frames. And this is basically like just a table of data. The values, so the values in a given column, I think, have to be all of the same type, but different columns can be of different types. They usually are, you can reference each column by its column name. You can provide row names to each of your data sets, or each of your rows. Yeah, values in each column have to be the same. And this is, by far the most dominant data structure that you're going to see in working in R. Here's a couple ways of actually reading in data. So if I kind of have a read.table, which kind of is free form, I can say, here's my ASCII file. It does have a header row. The row names are in column 1. I can just, once I load that in, I can just type worms and it'll spit out a representation of that table. It's a really big table, but I think it does the first 1,000 rows or something. Here's how to do subselection of data frames. So here, I'm returning every single row, but only the first, second, and third column. So it's always row, comma, columns. Yeah, so names are going to basically, I think, give me the column names of my data table. This can be kind of handy because we'll see how it simplifies how you actually reference your data in a minute, but you can attach a given data set at any time. So instead of doing, So normally, every time that you reference vegetation, you'd have to give it worms, $sign vegetation. By doing that attach function, it allows you to just say vegetation, and because you attached worms, it knows to look there for that name. So it just kind of, instead of having to do this, you could have just done worms, vegetation equals grassland. It just makes your code a little prettier. I think you can only really have, I guess you can have multiple things attached, but of course if there's conflicts and names, it's going to pick whichever one is attached second, and that can get a little confusing sometimes. So just something to be aware of. But here's an example. So you're saying, give me, okay, so when I do something like this, worms, vegetation equal to grassland, it's going to return a vector of logicals of whether that position in that column equal that value. And so what you can do is use that to do subselection in your data frame. So here I'm saying, for my worms data frame, return only the rows, so everything before the column, that are true, essentially. And so then you'll get only the things that are true. I think the sorting's kind of kludgy, to be honest, but here's an example of doing a return return everything, all rows, but order it by the values in the first column. So this is going to return things ordered by area. And then I'll return the first through 6 columns. I don't remember how many there are actually there. You know, so this kind of gets kludgy as you start. Like, if I wanted in descending order, I have to add this reverse order in worms. I think that's one area that could improve a little bit on data frames. It does have your basic if-else loop structures, pretty much the same as any other programming language. One thing to note is it's not tied to any kind of specific spacing of white space like Python is. You can put everything on more or less on one line or not, as long as you have the brackets in place. You know, here's your basic loop structure. Okay, but here's where we get into the more powerful type of structures that are different than what you would see in a lot of programming languages. So the first one is apply. The most basic version of this is apply. So what it's going to do is take, okay, here's my input. So I have a little data frame called M, it has these 2 columns. What I'm going to do is call apply, pass it in my data frame. The margin says either do it by row or by column. So I think 1 equals by row, 2 equals by column. Is that right? Yes. And I'm going to call this function sum. So for each input, give me the sum by row. So here you can see the output, so you can see each row and sums those 2 up. And here's the same type of thing doing it by the columns. Right? So that's, again, you don't see that a lot. The only equivalent I can think of is in Python. They have what's called list comprehensions that kind of do something similar. But it's really a feature of the language that a lot of people don't even know about. But for R, this is really at the heart of how it does stuff. This is how people write code. There's derivatives of the apply function. So lapply will basically return a list. So it'll pass in. So I'm going to pass in the numbers 1 through 5, call the function factorial, and get the output as a list. So the first element goes in, I get a list, a vector in my first element of my list, another vector at my second element of my list. So there's kind of a depth, a hierarchy of the return values here. Yeah, here's the actual function. So sapply is different in that it basically stands for simplify apply. And basically it tries to take whatever the output would be and reduce it, simplify it as much as possible. So instead of having this nested structure, it just returns basically a matrix of values. Because it decided that's the most simplistic version of the data I can return. So it does have kind of your nice basic summary function. So I can just call summary worms. I get, again, kind of similar to what we saw with pandas, you know, first, second, third quantiles, means, medians, max, etc. Gives you a very quick high-level view of your data. And then plotting, again, is pretty easy. So your basic plotting is going to be done through this plot function. So just plot area and soil pH. You get your basic plot. Not really very pretty, but you know, I haven't specified a lot of stuff here. Just plot these 2 variables. There's a whole ecosystem of different plots you can do, very similar to kind of what we saw in Matplotlib. Although I would say this is even more powerful and more flushed out than even Matplotlib. So here's an example of doing some graphing some graphical data, some network data. A lot of support for like geospatial type data and doing heat maps, etc. Here's where we're again looking at some of the assumptions behind our linear model to see if they're valid, constant residuals and normalized residuals, etc. And again, it's kind of similar to Matplotlib where there's a lot of things you have to do to make those plots happen, but somebody else has already done them, and you can just take what they've done and modify it. Yes?
So in terms of like if you wanted one programming language for plotting, what would you choose to learn over like?
I would go with R because it's easier, if that's really what you're wanting. Yeah.
What about versus like something like
Mathematica is great, but I'm always go towards open source free stuff, right?
Yeah.
It's gonna. I haven't done a lot in Mathematica or MATLAB or Octave. I've done a little bit in Octave, but they're fairly similar. But I would say, as a community as a whole, this is a more popular tool. So an important feature here is that I can save my work at any point in time. So here's kind of 3 different ways of doing that. I can just save the history out into a text file, essentially. So I can pass that. So if I did some really cool analysis, and I didn't want to just send them all the code and data, I could just send them the history file, the commands that I actually typed in. And again, I have that there for me if I need to go back and say, oh, exactly what did I do 5 days ago? I can go check the history file for that. I don't use that one a lot. I do use the save command. Save actually saves all of your environment into this kind of specialized binary proprietary R data file. So that when I load that back in, I get all the variables that I had, all the functions I'd already created, so on and so forth. And I think you get the history with that as well. I think that's saved in there as well. So this is the one that I use quite a bit. I can have control over exactly what I want to save. In this case, I'm just going to do everything in my environment. So ls returns everything that I have currently loaded. And then if I want to load it back later, I can run this command. So importing and exporting. So this is another place that R really kind of shines. It has, of course, your support for reading, delimited files, a lot of options. It has kind of some funkiness to it. You can tell exactly how it's delimited. In this case, it's tab delimited. Here's the file name on the import. Save it to this variable. Oh, I'm sorry. This is writing it back out. So write this. It's probably a data frame into this file using tab delineation. I really like the help functionality in R. So anytime I have a function and I want to see the documentation for it, I can just do $t.test, and it'll pull up this package, a full description of how to call it, what the arguments actually mean, and then usually towards the bottom, like some examples of people running it or some more in-depth documentation about how it works. When packages are put out on CRAN, which is the Comprehensive R something network, there's pretty stringent requirements for what your package has to provide, and one of them has to have good documentation, essentially. So even though there's like 6,000 packages out there, every single one of them has been at least a little bit peer reviewed to make sure that it's usable by the community. And again, that's where R really, really, really shines, is that there's 6,000 packages out there that no matter what you're trying to do, somebody's probably already done it. Really, the hardest part is figuring out which of those 6,000 you want to use. But there's usually ones that kind of bubble to the top of activity, right? The ones that most, the top 25 packages that people are using and everybody's using. And really, a lot of the other packages are derivatives of those, so they have some very specific way that they want to run a particular t-test or something, so they do their version of it, and only their research group will use it, but it's still useful to put it on CRAN because still their small 5 to 7 research team can pull it down from there. So here's how you would import a third-party library. So you just call library rpart. I don't actually know what that one does. If you do that and it says, oh, I don't know about rpart, then you can just go install that package as the name of the package you want. This is clearly out of date. That actually just goes to show you, I think Dr. Zhu created these slides about 18 months ago. So maybe it's doubled in 18 months. I don't know where he got that number exactly, but I know there's close to 6,000 now. So here's a web page that has all the available packages. And what's great is if one package depends on another, when I go to install that one package, it'll know to go install the dependencies as well. Very easy to install these packages. The one place where you get in trouble is a lot of these, same as Python, a lot of the performance improvements come from people writing C functions that are eventually called by R. So when you have a package that depends on the C or Fortran code under the hood, then it has to be compiled and linked to libraries. Your system may not have those libraries on it, so you may have to first go, and R can't handle that part of it for you. It can't do that. So you'll get some message like, oh, lib xxx.so or something is not found. Usually you can say, Google that message, somebody else has figured it out, oh, go do a yum install this particular devel package or something. That'll get you the dependencies you need on your system, and then you can rerun install.packages and that should work. This gets really complicated when you want to actually do it out on a system like Stampede, just because of the way our environment works. But our users can either, if we don't have a package pre-installed, they can try to install it into a local library. If they run into problems doing that, they can submit a ticket. I'm usually the one who will take those and go and actually install that into our default deployment of the packages we support. So here's an example of what I was saying. So if you're on one of our systems and you've never installed the package before and it's not already available, well, I can't write to the global repository of packages, but I can create a personal one in my home directory. Can actually start doing compiling C code under the hood, and I'll actually see that output when I'm installing it. So I kind of know that that's what's going on there. This is where I would see the errors if they were happening. And again, my colleague provided these links, these first three. So these are resources that he recommends for learning R. I think the best way to learn R, once you get kind of back past the basic syntax, is the site rbloggers.com. It's probably the site I go to the most throughout the week. And basically, it's a blog aggregator of all the people that are blogging about R. And usually those blogs are, hey, I have this simple little data set, I did this cool viz with it. It's usually about 3 to 4 paragraphs long, and it almost always includes the code that they had. So you can go grab that code, start playing with it, and you actually learn a lot that way. So that's actually what we're going to do now. Try to do. I need power. Are any of y'all able to actually install RStudio and other? Yes. I think I can reset. I'm going to put that in. Okay.
Well, I actually have both together for watching YouTube. No, I did
So for those of you that have R installed and you want to follow along with this, so here's rbloggers.com. So r-bloggers.com. And again, it's an aggregator, right? So they have just kind of little blurbs of all the latest articles. And we're actually going to play with one of these. So I found one. I guess the quickest way to get to it would be, there's a little search field here. So I can search for World Cup. And so I was playing around with this one recently. So this guy was looking at, let's go ahead and pull this up. So he found a bunch of information about the World Cup that starts in, what, 7 days in Brazil? So I actually went to the Wikipedia page. Let me make sure this is the right one, actually. Oh, sorry. Let's see another one about World Cup. Here we go. So simple analysis of a few aspects of the Wikipedia World Cup squads data. And so I like this example because it shows you how much data cleaning has to go into it before you can actually do the graphs. And then the graphs are actually pretty informative, just doing summary statistics. A lot of the way that people share data nowadays, code actually, is called a GIS. So it's kind of an offshoot of Git. which is the source control system that's out there. So what people will do is create these what are called GIFs, and they'll have sometimes a little README about what the file does, but then it just gives you the code, right? So here I can just I can click on raw, and it'll pull up this page. I can just copy and paste all this, and then go and dump it into a new, so I can start a new R script and just paste it in here, right, and get going. So I've already done this here. So this is RStudio. The resolution sucks, so I'm sorry that it's not bigger. These are incredibly expensive projectors, and they only show 1024 by like 760. It's ridiculous. But before I actually dig into the code, because I thought this was so cool, so he's actually basing this off of data that he found on Wikipedia, right? So Wikipedia is a great source for data. You don't obviously want to trust it. You don't want to necessarily write a research paper on it, but for playing with data, it's a great source, right? So basically this page just shows the team, yeah, so by groups, it shows each team in that group and all the players on the team and some basic statistics. So date of birth, how many caps they have, and what club they play for outside of the international stuff, right? So he, and I'm not exactly sure, I think that he, basically he created an output of that file, of this data, and I've missed exactly how he does that, but with most Wikipedia tables you can find like a more ASCII version of it that you can just copy and paste, but essentially he did that for us. So he created this big text file that looks like this, right? Let me see if I can show a better version of it. Okay, so this is what our source data looks like. This is what I'm talking about by semi-structured, right? This isn't exactly a CSV file. It doesn't have consistent structure on every line, but it has enough structure that I can write scripts that can parse out exactly what I want. Okay, so this is the source of all this analysis. I think that's how many international games you've played. So the more caps, the more experience you have in the international team. So what I did was just I grabbed that data off of that GIS site, and again, here's the. So the first thing I'm going to do is I'm just going to read that data in. So this is read lines, basically just reads each line of the text file and saves that as a basically list of free text lines, right? So I'm going to run that, look at it. Oops, crap. Do that. So right now I just have a whole lot of basically free text fields. So here's this line, so on and so forth, right? So it's still not usable yet. So the next thing he's going to do is run this command grep, which we looked at. He's going to look for this particular pattern, and then only return basically the positions in the file where that appears. So when you run code like this, if I do itab this command and it saves it to a variable, it doesn't actually output anything to my standard out. If I wrap that into colon or two parentheses, it'll actually run that command and output it. So it just kind of helps you, see what's actually going on. So here it's going to return a list of all the tabs where that particular field that I'm looking for start. I encourage you to play with this to see what each and every line does, because it's pretty interesting, and again shows you what kind of effort you have to go through to clean your data up to get it in a usable state. And I'm just going to kind of briefly go through it. Here I'm going to do something similar to find fields that are about the coaches. I'm going to save information about where country is, which in this case happens to be, I think, one less than where the coach tab begins in each line. I'm going to save a list of where things end and where they begin. And I'm going to create Okay. So let's see where we're at right now. So what does tabs equal? So again, over here in my environment, I can see what I have loaded in my environment. I can click on tabs to see what it actually looks like. Actually, let me start over. Make sure I clear my environment before I start messing with stuff. Start with a clean environment, run that. So I can quickly just highlight and run only what I've highlighted in my source editor. Oh yeah. So tabs is actually just setting up a blank data structure that I'm going to fill. And then here in this for loop, I'm going to go through and read through my main data, which right now is in D, it's still in D. And I'm going to extract information based on where I found those tabs to be. So that's actually pretty complex way of having to parse this data. Usually your data is in a format more like CSV where you can just kind of read it directly. But I think this is a great example of some of the effort you sometimes have to go through. So at the end of this, I'm going to have filled this tabs data structure, right? What that actually yeah. So now if I look at tabs, basically what I have is a list of 32 individual data frames. So let me pull this over. All right, so my first data frame is basically going to be all the Brazilian players. The second data frame is going to be all the Cameroon players, so on and so forth. So if I want to get, so I could say, tabs 1. And that just gives me all the Brazilian data players, and I could save that to an object if I wanted to. But it's kind of an interesting way of how we organize the initial data. Now I'm going to create this little function that allows me to do some kind of advanced ordering on the data frame. I'm just going to kind of skip through that. But here's a lot of cases of how you would do ordering. Something I didn't really go into over the R stuff is that another kind of first-class feature of R is what's called a factor. So when you have one of these fields that's like, a categorical or discrete field, you can actually turn it into what's called a factor, and that essentially allows R to do more efficient processing of it. Plus, it has some nice grouping features and stuff that are only available when you have a factor. There's certain functions that expect to have some of its input as a factor. So here he's actually creating a factor based on like positions, for example, the different positions people play. Here I'm going to load a library field. So if you're actually doing this, you probably don't have that. So here would be a case where if I'm in RStudio, I can just go up to install.packages. I can start typing in fields and say, okay, here's a package called that. I can click on it. And even if I have the package installed, I can still So it's under Tools on the main menu. Tools, Install Packages, yeah. So this might take a little while. Yep. Mm-hmm. Looks like maybe it's having a problem connecting to CRAN. Internet's still up. Yeah, so, okay, there it goes. I guess it probably tried a different mirror. So here I can see that it's actually, okay, so it's done, no errors. There's all the documentation that gets loaded. This is actually a pretty big package. And here I can see it's actually compiling Fortran code under the hood. So I don't really know what fields is. I could do $/fields. Actually, sometimes they have package level documentation, sometimes they don't. But I know that like this particular function is from that package. So I can see, or is it? Actually, no, I'm curious. Let me just pull it up real quick. can always, of course, go to CRAN. Just go CRAN fields and get the main description page for that package. So this is tools for spatial data, blobbity, blobbity, blobbity. So it does some stuff that he uses, right? So, okay. Here I think he's going to create basically, so now I'm getting into, I have my data in the form I want it, now I'm going to start doing some graphing. So I'm going to create a custom color palette that ranges between light blue and orange in 32 different steps. I'm going to bind all those tab things together to get this singular data, this singular D object. So let's actually look at what happens if we do that. So now I have D, which is all 736 observations of those 9 variables. So I can bind all those different data frames into one big data frame. Right. I'm going to do a little bit more cleaning. It looks like he's going to take some of these values. So like where league equals South, I want that to actually equal South Korea. Where it equals United, I want that to be United States. So he's looked through the data and realized there's some errors there. So I'm going to fix those here. I'm going to set the is home in away field. So if I look at what that is now, $. Those are all. Oh, he's going to. Oh, he specifies that, right? He's going to create these variables, or these, variables. Whether the person on this international team, whether or not they play in a league that's in their home country, essentially. So is this guy from Germany playing in the European League when he's not on his international team? So here's some examples of doing that. So kind of similar to matplotlib, the predominant plotting library that people like in R is called ggplot, or in this case, the second version of that, ggplot2. So first, let me make sure I ran all this. Okay. So here I'm going to load that library. And then ggplot2 again is one of those, grammar or graphics type packages where basically you have multiple calls to kind of build up your plot exactly how you want it. So I'm just kind of put these down on separate lines to see what it's doing. So right. So my basic plot is going to be, I'm going to plot a country. I'm going to group by country and plot age. I think fill is when you do the by. I want this to be a box plot, so I'm going to give it that geometry. I'm going to apply a particular theme. I'm going to add some labels. I forget how facet groups work. But basically, most of the rest of this stuff is just kind of making the plot look prettier. And that's going to actually save that plot information in this variable P1. Oops. Did it not like me putting that in a separate list? Try that again. Okay. I guess it didn't like that. All right, so if I actually want to see that plot, I have to go show P1. Then I'll actually plot it. All right, so here it's really small because it's going to fit my window, so I can just plot, zoom out, and boom. So this is actually pretty interesting. So this is looking at the 2014 teams, and it's going to do a box plot for each of those teams. So you can immediately see some pretty interesting things, like Colombia has these 2 major outliers. So box plots show the first to third quantiles, and then these lines represent any data in the first or second quantiles. So you can kind of get an idea if the distribution is right or left skewed. You kind of have to turn your head to the left, and if the top part is real long, that means it's a right skewed distribution. Anything that's in the very tail of the distribution is going to be considered an outlier. So we see some of these teams. This one has Iran has an unusually young player. Colombia has 2 unusually older players, etc. But for the most part, you're ranging in between the 25 to 30-year-old range. So, so kind of interesting to see. I'll close that for now. There was a problem with the second plot, so I'm going to skip that for now. I haven't had enough time to kind of play with it to see what's going on. And we'll talk about this library plier. So this is from the same guy that created ggplot2. And it's just another way of doing this classic, take my data, split it up, perform some calculations on it, and then glue it back together. So this is a pretty popular package. You'll see a lot of code that makes use of plier. I personally don't use it a lot. I can usually get away with using supply or things like that, but it may just be that I'm not fully taking advantage of the power of it, because it is extremely popular. But here we're going to create another graph. I think this one looks at, so we'll show P3. Yeah, so this one's pretty interesting. So this is looking at which of the club teams actually has the most players in the World Cup. So, you know, not too surprising. You see things like Bayern Munich, Spain's Real Madrid, England's Manchester United having the most players, right? They're the teams with the most money. They're able to buy the players they want when they're not playing for their international teams. But here's where we saw where we built that kind of custom color palette. You can do nice little features like that. And then I'm going to go ahead and create this just because it's going to want it in the last. Not find function. Oh, right. Okay. And then my last plot, which I think is the most interesting, if I recall correctly. So again, same kind of thing. I'm going to rearrange my data just a bit, give it a new color palette, call it ggplot2, and build up a nice plot. Show P4. Yeah, so this is kind of at the heart of what he wanted to look at starting off his analysis, right? He wanted to know, of all the people, you know, only the best players in the world play in the World Cup, right? So he's wanted to know from which league do those players go to. So predominantly England has the best players of all the leagues, followed by Italy, Germany, Spain, so on and so forth. And by, you know, quite a large margin, really. So kind of interesting. I don't know if any of you guys are big football fans, but the World Cup's always fun. Okay. I guess the last point I wanted to make is that you do also, of course, have the ability to do like multiple graphs per plot, I suppose. You can do that in base R using some particular features I won't go into here. Here he's using another third-party package, which I guess just makes it a little easier to do this. So here I'm actually going to plot all four of those on a single one. So, you know, that's what you might actually put into, you know, a presentation or something. But anyway, I thought that was kind of well, again, the scaling's still a little off, but you can play around with that, right? I thought that was a fun little example. I highly encourage, if you want to learn R, to just check out R bloggers, find something that looks fun. You know, I understand that I have a lot of experience with R, so maybe it's easier for me to do it, but I think if you just struggle through a couple of these, you know, it'll end up teaching you a lot about how to do things in R. I guess what I'm trying to say is you might start off with a more thorough introductory tutorial, but as soon after you get through with that, you'll start having some actual fun with data. A couple other things I wanted to bring to your guys' attention. If you're interested in learning more about machine learning, I highly recommend this Coursera course. So if you go to Coursera, I'll spell that right. Yeah, that's just slow. Type in Andrew Ng, Ng. So I took about 2/3 of this course, about a year and a half, actually before I started my master's program. And I highly recommend it. It's very well taught. He really concentrates on the algorithms and not all the ugly or difficult math behind it sometimes. At least when I took it, he was teaching it in Octave, which is an open source version of MATLAB. And it's similar enough to like R that I think you still get a lot of overlap with learning how to do things in these type of programs, right? This one actually starts June 16th, runs through the end of August. It's a very, very nice course, and you're going to learn a lot there. In general, edX and Coursera are very nice. I know that they have some courses, specific to, I think there's an intro to R, maybe not, statistics. So here's one from John Hopkins about just doing R programming. And it's really going to take something like this for you to really learn R to the depth that you'd be able to use it, right, on a daily basis. Like a one-day course in R is not going to be enough, right? You really need something that's kind of spread out. For one thing, so you get things in smaller chunks and you don't get overwhelmed. But this one, only 3 to 5 hours a week for 4 weeks. I haven't actually taken it, so I can't say how good it is. I have taken another John Hopkins one, which was using R to do health analysis, and it was pretty good. And I think it was by some of the same people. Oh yeah. So one other kind of resource out there. Have you guys ever heard of Kaggle.com? So particularly for Python. So this is like an online data analytics competition that they have. So there's all these different ongoing competitions they have. Some of them you can actually win money. Some of the others are just kind of for your own edification. One of them that's pretty nice is, so there's one from Data Science London, and it's all about learning Python and the scikit-learn framework. And basically, so it's been ongoing for a while, and I think it'll be ongoing indefinitely. But basically, you have this data set where you have a test set of, a training set of 1,000 samples. Each sample is going to be labeled either 0 or 1. It's going to have 40 features. And it's up to you to build a machine learning algorithm that can correctly predict the 9,000 test cases to figure out whether they should be 0 or 1. So it's an example of supervised learning where you have the test data that also has the correct labels already applied, and you can calculate your performance based on it. There's I don't know. I like having kind of a competitive way of going about learning a new language because it kind of gives you some motivation, right, to stick with it. So I recommend this one. That's a nice. Scikit-learn package is a pretty nice tool. I think that's it. I want to go home. I'm not exactly a talkative guy, so talking this much in one day, I'll probably lose my voice tonight. But you guys have been great. I think maybe they have something else to do, so I'm going to go run and get John real quick, and I'll be right back.
Thank you.
I live in an apartment with my girlfriend and my family.
Okay, so my friends, or my friend approaches is like threatening me because I'm going to switch my clothes. I want to switch the person I'm supposed to a couple. I mean, it's big, but it's just so she's like bitching that she doesn't feel uncomfortable with the guy. And I'm just like, first of all, I don't want to be rude, but first of all, I'm pretty sure he's not attracted to me. He's like super model. Second of all, like, there are couples, so I'm pretty sure they're going to come together. Like, when is he going to check? She's trying to argue with that he might, like, yeah, and I'm like, that doesn't make sense. So right now I'm just super livid because now I'm just like, it's a 2-2 apartment. So I want my other roommate to get pissed, but like, her freaking somebody's person is like, yo. Is your other roommate there? If there wasn't a problem with my roommate, my original roommate would not care. Like, we both had like we both
Oh, it is? Oh, that's just a. It really is challenging. Yeah, I was in
What type?
You
gave birth?
Yeah.
All right.
No, not yet. I didn't know. I thought you had like you were like. I didn't know you legit had. I just thought you kind of.
You like shades I'm like, oh, like, do you have
Yeah, they could. I mean, they probably cut it for like carbon scan.
but it's not like
There's a lot more complications. So far, it's going well, it's going to print. Like, what really nailed me is why I looked that up. Like, if you do,
you should go like something
oh my gosh, that would be very interesting.
or like you could send it to a
I was
car.
gonna be like, edit some home, put some skill into it, let's like search.
Yeah, yeah. Well, I mean, like get some like red stuff, like rough it up. Like,
Yeah.
Or like scan it to a car. And be like, oh God, you ran over my nose.
Oh yeah, dude, you can get some mad.
My mom had ever done that.
Like this shit is so stupid.
I didn't break any, but it was massive burn.
Really bother me if honestly, I would have given it for something to really want to.
No, I understand. Okay, because first she didn't want to die, so it was like, okay, I can understand that. But now she's freaking out about this and this straw, and I'm just like, I just
Yeah, you were
But I'm confused why it would be such a problem if they're a couple. And like, what would she do? Because like, there's been plenty of time. She would have then hated the other one. Because I'm like, what makes it different from the times when like I used to have like eczema, so I'm really confused as to even if I was to live there. I'm just gonna, that's honestly what I'm gonna do. I'm just gonna, like, I don't even know why I asked her here, because then she would have never known.
Yeah, you should just not send anything and then think to yourself. You could really do anyone.
I'm gonna do a lot of things once I finally normal things. I mean, I can, like I said, I can go on a segment. Or a segment is fish food. It actually has a little thing. So like it doesn't hurt the bone at all. The only time it really hurts is like thinking like you stuff your I just can't.
Well, that would be I don't
I'm assuming not. I don't think you're right.
We can't share stuff like that.
It looks like Spark, right? It's like basically Spark. I really do want to go to like this is a phone right here. That one is about me. What?
Yeah.
But this one is about me. That's the second one. All those inside.
So are you just like missing your like very
second deep road.
Yeah, I already worked it
Because so basically,
oh, so they just like okay.
they deload it, so they don't just
Oh wait,
control
no,
it.
not you.
Yeah, they actually kind of.
Okay. was a little like there. So
We should be.
little like
skeletal.
Yeah, skeletal.
On the, done program.
We should be done.
We're not ever not.
Not gonna do that. Okay.
Go to the skeleton of the
Wait, no, this is the other.
I bet.
Here.
What is
It's pretty much exactly like that.
I just installed one.
It's
How did you get
yeah, but right there.
Well, I'm using
No. Saturday morning, right?
I'm so sorry.
The phone has so much air in it.
Right. Like that whole guy that connects his arm off. Like, you know,
Oh,
the
you're talking about the
everyone,
movie,
like,
the true story where the guy goes on.
Yeah, imagine if you were on the pocket of this, like the amount of like.
Thing you went through?
Yeah, the amount of resolve. He said, because you're saying like you should see that there, and like when you cut through it, holy guacamole.
There's holy guacamole.
Awful.
You can't use cigarettes.
Did you say you used Ubuntu? What if I switch back to C? Are you using Ubuntu? Which one?
Yeah, you can put this in your
Just gotta wait for it to heal. I get my second box.
Oh, you have
Maybe it's the only thing I really can't use.
What kind of
I don't think a second or so.
I mean, I guess
I
you
couldn't
can
back
back
up.
Yeah.
The second one will. But this one is more,
Oh,
more like tough.
I know. You get an iPad.
Yeah. I know you want the text to be like.
Really, I really don't want to hear that. So I chose.
Oh.
Wait, you guys did a picture of that?
Yes, we did. Where'd you go?
I totally forgot about that. Well, I had a good I totally forgot.
Maybe, but I like.
Yeah, it's not me.
No, we did it actually. We did it actually.
And then you have my friend from
After that.
And then I saw this girl, this guy, and he wants like so there's something that and he wants to and then it's not this girl with pet chocolate. I was like,
What's your name?
Like the same as other group, except there's just an A after.
Sister pages are replaced.
Huh? Yeah, is it this right?
Okay, so what are we, guessing your number?
Yeah. That's where he gave us to download.
So what are we doing? What operating system?
Windows.
Just use the right, use whatever you want.
It might have been 32 or 6. Exactly, it makes it match.
Yeah, we can.
Are you sure you want to use it?
We're using 64. Let's see what. I couldn't find them, but it was weird. It was like yeah, go for it. I think you know.
Oh, sorry. Well, maybe he gave us a bad one. Yeah, that PowerShell thing that took you off, I was like, in those spots.
Yeah, maybe.
Oh, it's just.
Which application did you say you were working with?
For this project,
Sorry.
Dr. You know?
Not personally, but I know she's one of them.
No, the one who I did the bit with was the doctor. It just works for workflow. It just makes it's just I took a networking class with her, but I feel like I learned more skill than I understand that there are actually but also except for how to play what. Oh, do you need my path? There's
Okay. So. Well, it probably just wasn't on your path. Maybe this is off.
I think I had a different folder for the file.
Yes.
It doesn't matter what.
Do you use Java for your?
Yes. I do want to read some.
I.
Yeah, so what you want to do is just add this to your path. You know,
Well, let's see this.
I'm going to do
Oh, yeah. Yeah. And then it's and in my
oh, it's got it. Users. Oh, it's looking at users. You have it in C type.
oh. I was like, I feel like this before. So that's how
This is where Linux shines.
Wait, no, red.
Okay, I'm on a bunch right now. It's like lightning.
Hey, you may need your straight offs. Like I went to Fedora or KDE and like the browser just won't work for one day.
Yeah.
With Linux update. I can live with it.
I can probably listen to you guys use a lot of
What's that?
you guys use a lot of the Nord CFD.
Well, yeah, it's CentOS, right? And all the big systems. I like being able to install stuff when I can do the same way.
I like being able to follow tutorials, but I think it's fine. Like, why do you think this is so cool? Yeah.
Yeah, Sigmund's almost not worth the effort. If you do want to do stuff like that, you might try like virtual blocks and just running them in VM, just running Linux. I did that for
Oh, I have. Oh, wait, did I uninstall it? I think I might have uninstalled it just because it took a lot of time.
I was not the one.
That's weird. I think it took off version.
Can I have a big card?
That's better than using Sigmund, in my experience.
I feel like Sigmund doesn't even work.
They have the code.
It
It's
just
different
shows
enough from Linux that you don't really get all the details. I'm gonna look for John in here real quick.
Cool.
Are you good, buddy? Think you got what you need?
Yeah.
Was he making a phone?
No.
If you guys had somebody come
Well, he was about he was a little before it. I don't know what was that.
oh, yeah, he was.
Data science.
Okay, once I have Python, what do I have Python? Is it like, where do I put it?
How's everyone doing? Alright, so we don't have an email form, but do not be surprised if John sends you a link or one of us sends you a link. We just ask that you please complete it. We just kind of want to get a feel of, you know, how the training went, what areas were most helpful, you know, how the facilitators did, or the instructors, the researchers that were here, spending much of their valuable time, you know, facilitating the training. But with all that said, we're going to dismiss you guys, and then tomorrow, again, it's at the Viz Lab, so it'll be closer to campus. I believe the first presentation is at 10 a.m., right? Is it? Yeah, all of tomorrow's in the Viz Lab, and there's 3 presentations. I believe one at 10, 11. Oh, you get to, well, yes. Yeah, I didn't say that out loud. You probably want to, you know, wake up early and start reviewing all the important training material from this week. But I know that you all have been working really hard and stayed up late on Tuesday for the Austin Forum. So we do expect you to be there tomorrow. I won't be there, but Eddie, his name's Eddie, and he'll introduce himself to you. He's the Viz Lab manager. Will be there to, you know, help set up. He'll also be meeting a lot of the. Thank you, David. Thank you. Sorry about that. David Walling actually just finished his PhD as well. He's been here for a few years and took time off to do that as well. Anyway, so tomorrow you do get a lunch break in between. Check on the email that Lisa sent you. If you're dine-in dollars, I do believe they're accepted at the it's called O's Campus Cafe.
I don't think
I don't think so.
Are you kidding me?
nothing makes our dollars like that. But I mean, that's done this way to non-campus.
Because like those summer sessions started, so lots of places are opening.
Okay.
Yeah.
Well, if you don't want to take a hike and get other places, there's the O's Campus little cafe, which is literally in the ACES building, and they have pretty good options as well. And then I do recommend you kind of walk around the computer science building for the non-UT students. It's connected to the ACES POB building. But what was that?
Oh, I see the shortcut.
Oh, the shortcut. Lola's going to give you a tour? Just kidding. I'm just kidding. I'm kidding. I'm kidding. But yes, please enjoy. We'll make sure you guys catch the train. And if you need any supplies, any resources from here until Monday, please let me know. Thanks, guys.
We're not coming here
At all. So you show up at 11. Huh? No, be on time though. What I do recommend, if you want to arrive a little before 11, I mean, eventually you'll get a little tour of the Viz Lab. If you could be there at 10, it would probably be better, or 10:30, just so that you could walk around and get a little tour of the Viz Lab if you have.
Casual attire.
Yeah, I would say casual attire is fine. Presentation. Everything went well today?
Yeah. It's like it progressed from like almost purely hands-on to like almost purely verbal towards the end, but yeah, it was pretty cool. The machine learning aspect, I think, was interesting.
Really?
Yeah.
Out of the whole week, what's been your favorite?
The day that we did something with the code for and then.
See a minute. Shell scripting?
Yeah.
Cool. Cool.
Yeah, you can just write little stuff like one liner, like while you're on the command line.
Nice. You guys are gonna have fun at the Viz Lab.
I've heard it's a really beautiful place.
It's awesome. You get to play. Yeah.
Really?
You get a lot of hands-on interaction.
Oh.
That's where we have most of our our high school tours and middle school tours that the kids don't want to leave. It's real fun.
I thought that was TACC
What's that?
at first. I thought that was TACC at first.
It is. It's the Viz Lab. Eventually, what's going to happen is in the next maybe year, we're going to start breaking ground on the new project expansion project. So we're going to have an annex building that's going to connect from one of our corridors at the very end. They're going to break the wall and they're going to build a corridor to a new building because we ran out of office space. And we're going to bring the Viz Lab there too, like so that we can have more of a, more of the average activity here versus on campus. So we can have it. No, someone's gonna get the computer, so you just want to make sure that you hook up your own laptop to your own computer. You make sure you don't leave anything behind. I have Jamila, I have your folder, I don't know why, from the summer school.
I think you picked it.
I do. Yes, I have it. I'm so sorry.
Sorry.
Okay.
Rosie, can we take a drink?
You can drink them. Yeah.
We should take them. Or do you need?
They're open, what's gonna happen is they just put them in the kitchen and whoever from the staff will put it on something they drink it, but if you wanna take, we'll take it. If it's closed, set it. But all the
I'll
other
do
stuff,
that.
yeah,
I'll take this.
yeah.
Everyone does, they just want to go.
Maybe the same one as the-
Thank you guys. A lot of information, huh? You're gonna love it tomorrow. Tomorrow, I think tomorrow's gonna be the most fun out of the week. It's all hands-on, it's visual, if you want to take a note, I'm putting you back around the house, and you just plug it anywhere, something you should definitely check out. I know that you got the idea of a product for this dinner, but that's a good place for like, some really beautiful stuff. Then I can go